the night sky reveals the Milky Way, a broad band of light made up of hundreds of billions of stars. Each point of light within that pale band is a sun, and many of them may have planets orbiting around them. This glowing stretch of stars is our home in the universe, a massive spiral galaxy surrounded by vast regions of empty space. Yet behind its impressive appearance lies a fact that challenges humanity's greatest ambitions. Despite all our progress in science and space exploration, we remain confined within this galaxy. No matter how advanced our technology becomes, the immense distances, the limits set by time, and the fundamental laws of physics make travel beyond it almost impossible. Could it be that the universe has already defined how far we're able to travel? Before we dive in, drop it in the comments below where in the world you're watching from, and what time it is there now for you. We're always excited about hearing where our viewers are tuning in from. The Andromeda Galaxy is one of the most fascinating and breathtaking sights in the night sky. It is a barred spiral galaxy, meaning that its spiral arms stretch out gracefully from a bright bar-shaped core, and it is the nearest large galaxy to our own Milky Way. Long ago, before astronomers understood what galaxies really were, Andromeda was called the Andromeda Nebula. Today, it is officially listed in several astronomical catalogues as Messier 31 and NGC 224. This colossal galaxy has an enormous diameter of about 152,000 light-years, nearly twice the width of the Milky Way, which makes it the largest member of our cosmic neighbourhood, the local group of galaxies. It lies at a staggering distance of roughly 2.5 million light-years from Earth, or about 765,000 parsecs in astronomical terms. To put that into perspective, the light you see from Andromeda tonight actually began its journey toward us around 2.5 million years ago, back when early humans on Earth were first learning how to shape simple stone tools. The name Andromeda comes from the region of the night sky where it can be seen, the constellation Andromeda, named after a princess from ancient Greek mythology who was rescued by the hero Perseus. Thus, this galaxy carries not only a scientific identity but also a mythological one, connecting the stars to the oldest stories told by humankind. In terms of sheer mass, the Andromeda Galaxy is roughly equal to the Milky Way. Each is believed to weigh around 1 trillion times more than our Sun, an unimaginable figure of about 2 × 10 to the power of 42 kilograms. For a long time, scientists believed that Andromeda was significantly heavier than the Milky Way, perhaps by 25 to 50%. But more precise research in the early 21st century revealed that the two galaxies may be much closer in mass than once thought, and in fact, the Milky Way might even be the heavier one. Astronomers also know that these two galactic giants are not standing still. They are slowly being pulled toward each other by gravity. In roughly 10 billion years, they are expected to collide and merge into one enormous new galaxy, possibly forming a bright, round elliptical or a smooth, lens-shaped lenticular galaxy. This future cosmic dance will dramatically reshape our night sky, though by that time, our Sun will likely have evolved into a red giant, and Earth as we know it may no longer exist. Even now, Andromeda is one of the brightest deep sky objects visible from Earth. With an apparent magnitude of about 3.5, it can be seen without any telescope on a clear, moonless night, even from places with moderate light pollution. To the naked eye, it appears as a faint, misty patch of light, a ghostly glow stretching across the dark. Ancient civilizations may have noticed it long before telescopes were invented. Some historians even believe that the ancient Babylonians may have recorded Andromeda as part of a constellation they called the Rainbow of the Sky. The first clear written description of Andromeda comes from the Persian astronomer Abd al-Rahman al-Sufi, who, around the year 964, described it in his Book of Fixed Stars as a small cloud or nebulous smear. This was more than 1,000 years ago, and it remains the earliest known record of a galaxy other than the Milky Way. For centuries after, astronomers referred to it as the Little Cloud. In the early 17th century, in the year 1612, the German astronomer Simon Marius gave one of the first telescopic descriptions of the Andromeda Galaxy. Later, the British astronomer John Flamsteed catalogued it as 33 Andromedae. In 1745, the French scientist Pierre-Louis Maupertuis proposed a bold idea, that this fuzzy patch of light might actually be an island universe, a distant system of stars separate from our own. Then, in 1764, Charles Messier added it to his famous list of celestial objects as M31. Messier mistakenly credited Marius as its discoverer, even though Andromeda had been visible to the naked eye since ancient times. By 1785, the great astronomer William Herschel noticed that Andromeda's core had a faint reddish colour. He believed it was the closest of all the great nebulae, and based on its brightness, he guessed it was about 18,000 light-years away, which, though inaccurate, was an impressive attempt given the tools of his time. In the mid-19th century, in 1850, William Parsons, also known as the third Earl of Rosse, made one of the first drawings showing the spiral structure of Andromeda. This was a major step forward in understanding that some nebulae were not mere clouds of gas, but vast star systems with organised shapes. Then, in 1864, another astronomer, William Huggins, examined Andromeda's light using a spectroscope and found something remarkable. Its spectrum did not resemble that of a gas cloud, but looked much more like the combined light of countless stars. This discovery hinted that Andromeda was in fact made up of stars, a galaxy, not a nebula. In 1885, a bright new point of light flared up in Andromeda, a supernova, though astronomers of the time called it Nova 1885 because they had not yet distinguished between novae and supernovae. This was the only supernova ever recorded in Andromeda. Then, in 1888, the astronomer Isaac Roberts captured one of the first long-exposure photographs of Andromeda. His image revealed its spiral structure in stunning detail, though he still believed it to be part of the Milky Way, a mistake common in that era. By the early 20th century, astronomers began to gather evidence that would change everything. In 1912, Vesto Slipher used spectroscopy to measure Andromeda's motion. He found that it was moving toward us at a tremendous speed of about 300 kilometers per second, faster than any other object yet measured. This marked the beginning of a new understanding of galaxies as independent, massive systems scattered across the universe. Interestingly, the philosopher Immanuel Kant had already proposed this idea as early as 1755. In his Universal Natural History and Theory of the Heavens, he suggested that the Milky Way was just one of many island universes, galaxies, floating in the vastness of space. His visionary thinking anticipated discoveries that would not be confirmed for more than a century and a half. In 1917, another breakthrough came when the American astronomer Heber Curtis studied a nova in Andromeda and found 11 others in older photographs. He noticed that these novae were about 10 times fainter than similar ones seen elsewhere in the sky. From this, he calculated that Andromeda must be about 500,000 light-years away, much farther than the edge of the Milky Way. Although this estimate was still lower than the true distance, it was close enough to suggest that Andromeda was not a nearby nebula, but a separate galaxy altogether. This discovery strengthened the island universe theory, the idea that the universe is filled with countless galaxies, each shining with its own billions of stars. Andromeda, once thought to be a mere cloud in our cosmic backyard, was revealed to be another grand spiral galaxy like our own, crossing the infinite darkness of space alongside us. In the early part of the 20th century, the universe as we know it was still a mystery, and one of the most famous scientific disagreements in history took place. In the year 1920, two astronomers, Harlow Shapley and Heber Curtis, faced off in what became known as the Great Debate. They argued passionately about the true nature of the Milky Way, the mysterious spiral nebulae seen through telescopes, and the overall size of the universe itself. Curtis defended the bold idea that the Great Andromeda Nebula was not part of our own galaxy, but an entirely separate island universe, a galaxy in its own right, lying far beyond the Milky Way. To strengthen his claim, he pointed out the dark lanes running through Andromeda, which closely resembled the dust clouds seen in our own galaxy. He also referred to earlier measurements of Andromeda's Doppler shift, which showed that it was moving in a way consistent with being a separate distant system, rather than a nearby cloud of gas and stars. Just 2 years later, in 1922, the Estonian astronomer Ernst Öpik developed a clever method to estimate how far away Andromeda really was. By studying the motion of its stars, he calculated that it must lie about 450 kiloparsecs away. That is roughly 1.5 million light-years, placing it well outside the Milky Way. This was a revolutionary idea at the time, suggesting that our galaxy was not the entire universe, but only one among many. Then came Edwin Hubble, who forever changed our view of the cosmos. In the year 1925, using the giant 100-inch Hooker telescope at Mount Wilson Observatory, he identified special stars called Cepheid variables within Andromeda. These stars brighten and dim at regular intervals, allowing astronomers to calculate their true distances. Hubble's photographs and careful measurements revealed beyond doubt that the Great Andromeda Nebula was not part of our galaxy at all. It was a separate galaxy, millions of light-years away. This discovery ended the Great Debate and expanded humanity's understanding of the universe in a single breathtaking leap. 2 decades later, in 1943, Walter Baird became the first person to clearly see individual stars in the central region of the Andromeda Galaxy. With careful observation, he discovered that the stars there belonged to 2 distinct groups: the younger, hotter and faster-moving stars in the galactic disk he called Type 1, while the older, cooler and redder stars in the central bulge he named Type 2. This classification, later used for stars in the Milky Way and other galaxies, helped astronomers understand that galaxies evolve and age just like stars do. Baird also realized there were 2 types of Cepheid variable stars, which meant that previous distance measurements, including those to Andromeda, had been underestimated. When he corrected the calculations, the distance to Andromeda and the entire scale of the known universe effectively doubled overnight. By the middle of the 20th century, new technology allowed astronomers to study galaxies in ways that went far beyond visible light. In 1950, Robert Hanbury Brown and Cyril Hazard at Jodrell Bank Observatory detected radio waves coming from the Andromeda Galaxy for the first time. A few years later, in the 1950s, John Baldwin and his colleagues at the Cambridge Radio Astronomy Group created the first radio maps of Andromeda, revealing energetic processes invisible to optical telescopes. The galaxy's bright core became known in the second Cambridge Radio catalogue as 2C56. Then, in 1959, astronomers André Lallemand, Monsieur Duchenne and Merle Walker discovered that the central nucleus of Andromeda was rotating rapidly. Using the 120-inch telescope and Lallemand's advanced electronographic camera at the Lick Observatory, they estimated that the nucleus had a mass of roughly 13 million times that of the Sun. Just 2 years later, in 1961, Merle Walker found a similar rotating nucleus in the small companion galaxy Messier 32, with a mass close to 10 million suns. These discoveries were early hints that something extraordinary lurked at the centres of galaxies, what we now recognise as supermassive black holes, powerful engines driving galactic cores. As the decades passed, new discoveries continued to reveal Andromeda's hidden wonders. In the year 2009, astronomers detected a subtle event called microlensing, where the light from a distant object bends due to the gravity of a massive body passing in front of it. This rare occurrence might have been the first sign of a planet within the Andromeda Galaxy, an astonishing possibility showing that worlds could exist even in other galaxies far beyond our own. In the year 2020, observations made with several great radio telescopes, the Westerbork Synthesis Radio Telescope, the Effelsberg 100-meter radio telescope, and the Very Large Array, unveiled something even more fascinating. They found that Andromeda's magnetic fields were neatly aligned along a vast 10 kiloparsec wide ring of gas and star formation, showing that magnetic forces help shape the galaxy's majestic spiral structure. Only a few years later, in 2023, a remarkable discovery came not from professional scientists but from a team of dedicated amateur astronomers, Marcel Drexler, Xavier Strotner, and Jan Sainty. They spotted an enormous faint nebula rich in oxygen, located just south of the Andromeda Galaxy, near the bright star known as 35 Andromeda. The nebula, later named SDSO-1, was so dim that it required dozens of hours of exposure time to capture its ghostly glow, which appeared to shine only in the light of doubly ionized oxygen. At first, researchers believed SDSO-1 might be an object lying outside the Milky Way, perhaps created by the interaction between the halos of our galaxy and Andromeda's. However, later studies using spectroscopy revealed that the nebula is actually within our own galaxy. One recent explanation suggests that it may be a bow shock, a glowing arc of gas formed by the motion of a dying binary star system called E.G. Andromedae through surrounding interstellar material. In the year 2025, the National Aeronautics and Space Administration unveiled one of the most detailed portraits of Andromeda ever made. Using over 600 separate images taken by the Hubble Space Telescope, over a decade of careful observation, scientists created a massive mosaic showing hundreds of millions of individual stars. Using over 600 separate images taken by the Hubble Space Telescope, over a decade of careful observation, scientists created a massive mosaic showing hundreds of millions of individual stars. Among them, about 200 million were brighter and hotter than our Sun, yet this still represents only a small fraction of Andromeda's total star population. The result is a breathtaking window into another galaxy, our nearest great neighbour, vast, ancient and endlessly mysterious, a reminder of how far human curiosity has carried us into the depths of the cosmos. In the middle of the 20th century, our understanding of the Andromeda Galaxy took a great leap forward. In the year 1953, astronomers discovered a second, dimmer kind of Cepheid variable star. This important finding doubled the estimated distance between our Milky Way and the Andromeda Galaxy. Later, in the last decade of the 20th century, scientists used data from the European Space Agency's Hipparcos satellite to refine these distance measurements even further. By studying both red giant stars and red clump stars, they were able to improve the calibration of the Cepheid distance scale and bring new accuracy to our understanding of just how far Andromeda truly lies from us. Billions of years earlier, a dramatic cosmic event had shaped the Andromeda Galaxy itself. Between about 2 and 3 billion years ago, two large galaxies collided in a spectacular merger near the region where Andromeda now lies. The two galaxies were not equal in size. The larger one was roughly 4 times more massive than its partner, but their violent union left lasting marks that can still be seen today. The discovery of this ancient merger came from studying Andromeda's stars and noticing something strange. Their ages and movements did not match what would be expected in a calm, stable galaxy. Astronomers found that around 2 billion years ago, star formation across Andromeda's vast disk had been far more intense than it is now, evidence of a cosmic upheaval in its past. Through complex computer modelling, scientists recreated this galactic collision and learned that it likely produced many of Andromeda's present-day structures. The merger seems to have formed the galaxy's metal-rich halo, the giant stellar stream, and both its thick and thin disks. It may even have created a vast circular ring about 10,000 parsecs from the galaxy's centre. During that violent era, Andromeda's rate of star formation was so high that it briefly became what astronomers call a luminous infrared galaxy, shining brightly in infrared light for roughly 100 million years. These same models also reproduce the shape of Andromeda's central bulge, its large bar-like structure, and the overall density of its outer halo, showing how one ancient collision sculpted much of the galaxy we see today. For some time, researchers believed that Andromeda and the smaller Triangulum Galaxy, also known as Messier 33, might have passed very close to one another between 2 and 4 billion years ago. However, more precise measurements from the Hubble Space Telescope later suggested that such a close encounter was unlikely. Determining the true distance from Earth to the Andromeda Galaxy has long been a challenge for astronomers, and over the decades, at least 4 different methods have been used. In the early years of the 21st century, new techniques brought even greater precision. In the year 2003, scientists used a method known as infrared surface brightness fluctuations and adjusted their results for metallicity effects, producing an estimate of about 2,570,000 light-years. The following year, using the classical Cepheid variable method, they arrived at a slightly smaller value of roughly 2,510,000 light-years. Then, in the year 2005, astronomers made a remarkable discovery, a pair of hot blue stars in Andromeda that formed an eclipsing binary system. By carefully measuring how the stars dimmed as they passed in front of one another, scientists could calculate their exact sizes and brightness. From these values, they determined the distance to the system to be about 2,520,000 light-years, placing the whole Andromeda Galaxy at roughly the same distance. Another method, called the tip of the red giant branch technique, gave a similar result of 2,560,000 light-years. When all these measurements were combined, the average distance to Andromeda was calculated as approximately 2,540,000 light-years from Earth, a distance that modern astronomers still accept with high confidence. For many years, the mass of the Andromeda Galaxy was also the subject of debate. Until the year 2018, most estimates suggested that the entire halo of Andromeda, including its vast amount of dark matter, was about 1.5 trillion times the mass of our Sun, somewhat larger than the Milky Way's estimated 800 billion solar masses. Earlier studies, however, had hinted that both galaxies might actually have very similar masses. Then, in 2018, new radio observations supported this earlier idea, indicating that the Milky Way and Andromeda are likely close to equal in total mass, each containing around 800 billion solar masses. Other studies in the early 21st century revealed that Andromeda's spheroidal component is denser in stars than that of our own galaxy, and that its stellar disk stretches to nearly twice the diameter of the Milky Way's disk. The total mass of Andromeda, depending on the method used, is thought to fall somewhere between 800 billion and a little over 1 trillion solar masses. Of this, between 10 and 15 times 10 billion solar masses consist of stars, with nearly 1/3 of them concentrated in the central bulge, a little over half in the galactic disk, and the rest scattered throughout the halo. By the year 2019, newer analyses based on escape velocity and dynamical measurements placed Andromeda's total mass at about 800 billion solar masses, roughly half that of the Milky Way, which by then was estimated to have a mass of about 1.5 trillion solar masses. Besides its countless stars, the Andromeda Galaxy contains enormous amounts of gas and dust. Its interstellar medium holds at least 7 billion solar masses of neutral hydrogen, more than 300 million solar masses of molecular hydrogen within its inner 10,000 parsecs, and around 50 million solar masses of dust. Surrounding the galaxy is a gigantic halo of hot gas, almost invisible to the eye but incredibly vast, stretching nearly 1 million light-years into space, about halfway toward our own galaxy. This immense halo may contain about half as much mass as all the stars within Andromeda itself. Astronomers believe this halo formed around the same time as the galaxy, enriched by heavy elements created in countless supernova explosions. Every time a massive star in Andromeda's disk ended its life in a brilliant supernova, it hurled elements like carbon, oxygen and iron far into space, gradually filling the halo with this cosmic debris. Over billions of years, nearly half of all the heavy elements ever produced by Andromeda's stars have been blown far beyond its visible disk, which spans about 200,000 light-years. The Andromeda Galaxy shines with an estimated brightness of about 2 6/10, times 10 to the power of 10 solar luminosities, meaning it radiates roughly 25% more light than our own Milky Way. However, because it appears at a steep angle when viewed from Earth, a large amount of its light is hidden by interstellar dust drifting through its vast spiral arms. This makes it difficult for astronomers to determine its true brilliance with precision. Some scientists suggest that Andromeda may even be the second brightest galaxy within a region stretching 10 megaparsecs around the Milky Way, surpassed only by the elegant Sombrero Galaxy. Its absolute magnitude has been estimated at about -22.21, though different studies have given slightly varying results. In the year 2010, observations made using the powerful Spitzer Space Telescope revealed that Andromeda's absolute magnitude in the blue part of the visible spectrum is around -20.89. With a colour index of +0.63, this corresponds to an absolute visual magnitude of about -21.52, compared to roughly -20.9 for the Milky Way. At that wavelength, the total luminosity of Andromeda was estimated to be about 3 64/100 times 10 to the power of 10 solar luminosities, making it one of the most luminous galaxies in our cosmic neighbourhood. Despite its brilliance, Andromeda's current rate of star formation is surprisingly modest. Each year it produces only about 1 solar mass's worth of new stars, whereas the Milky Way gives birth to roughly 3 to 5 solar masses in the same amount of time. Even the rate of novae, stellar explosions that briefly light up a galaxy, is about twice as high in our own Milky Way compared to Andromeda. This suggests that Andromeda likely went through a glorious era of intense star formation long ago but is now resting in a quieter phase of its evolution. Meanwhile, our Milky Way continues to blaze with more youthful energy, filling its spiral arms with fresh stars. If this pattern persists, the total brightness of our galaxy might one day surpass that of Andromeda itself. Modern research places the Andromeda Galaxy in what astronomers call the Green Valley on the galaxy colour magnitude diagram. This region is a transitional zone between the blue cloud, which contains galaxies still busy forming new stars, and the red sequence, where older galaxies have almost ceased star production altogether. Galaxies in the Green Valley, like Andromeda and our own, are slowly running out of the gas and dust needed to create new stars. In computer simulations of galaxies resembling Andromeda, star formation is expected to fade completely within about 5 billion years, even after accounting for the temporary burst of new star creation that may occur when Andromeda and the Milky Way eventually collide and merge. In visible light, Andromeda is classified as an SA's B galaxy in the Globular sondage system, a way astronomers categorize spiral galaxies based on their shape and structure. Yet data gathered from the 2-micron all-sky survey and the Spitzer Space Telescope in the infrared part of the spectrum revealed a hidden truth. Andromeda, much like the Milky Way, possesses a central bar structure. This elongated bar is tilted about 55 degrees counterclockwise from the main disk, shaping the galaxy's graceful spiral pattern. Astronomers have long debated how to define the exact size of a galaxy, since different measurement methods often yield different answers. One widely used standard is the D25 esophote, which marks the region where the brightness of the galaxy's blue light drops to 25 magnitudes per square arc second. According to the Third Reference Catalogue of Bright Galaxies, published in 1991, Andromeda's D25 diameter measures about 46 and 56 hundredths kiloparsecs, which is roughly 152,000 light-years, at a distance of about 2.5 million light-years from Earth. An earlier estimate made in 1981 gave a slightly larger diameter of 54 kiloparsecs, or about 176,000 light-years. In the year 2005, observations from the Keck telescopes revealed a faint ghostly halo of stars surrounding Andromeda, stretching far beyond its bright spiral arms. These stars in the outer halo move in a disorganized manner, unlike those in the galaxy's main disk, which follow more orderly orbits moving at about 200 kilometers per second. This diffuse halo extends outward to a diameter of roughly 67 and 45 hundredths kiloparsecs, which equals about 220,000 light-years, an immense sphere of faint starlight enveloping the galaxy. From our point of view on Earth, Andromeda appears tilted at an angle of about 77 degrees. If it were tilted to 90 degrees, we would see it perfectly edge-on. Detailed analysis of its structure reveals that Andromeda's disk is not perfectly flat, but instead has a pronounced S-shaped warp. Astronomers believe that this warp may be caused by the gravitational pull of nearby satellite galaxies. One possible culprit could be the smaller galaxy known as Messier 33, whose tug may be slightly twisting Andromeda's majestic spiral arms. Through careful spectroscopic studies, scientists have been able to measure how Andromeda rotates at different distances from its bright core. Near its center, about 1,300 light-years away, the stars rotate at a speed of roughly 225 kilometers per second. Farther out, at a distance of 7,000 light-years, the speed drops to around 50 kilometers per second, before rising again and reaching a maximum of 250 kilometers per second at a distance of about 33,000 light-years from the center. Beyond that, the rotational speed gradually declines, falling to about 200 kilometers per second at a distance of 80,000 light-years. These velocity patterns indicate that Andromeda contains a highly concentrated mass, around 6 times 10 to the power of 9 solar masses, within its nucleus, with total mass increasing steadily outward to about 45,000 light-years before tapering off more slowly. The spiral arms of the Andromeda Galaxy glow with the light of numerous H2 regions, vast clouds of hydrogen gas ionized by newborn stars. These luminous zones were studied in remarkable detail by the German-American astronomer Walter Baade, who described them as appearing like beads on a string. His detailed observations revealed 2 elegant spiral arms that, though tightly coiled, are spaced more widely than those of our own Milky Way, giving Andromeda its distinctive, graceful shape as it sails across the dark sea of space. The Andromeda Galaxy, seen from Earth at a sharp angle close to edge-on, hides much of its true spiral beauty behind its tilted appearance. Because of this, astronomers have found it quite challenging to study the exact shape of its spiral arms. However, when scientists used special rectified images to straighten its appearance, the galaxy revealed what seemed to be a fairly ordinary spiral form. 2 vast trailing arms curl gracefully around its bright core, each one separated by at least 13,000 light-years, an unimaginable gap of about 820 million astronomical units. These arms can be traced outward beginning from roughly 1,600 light-years, or 100 million astronomical units, from the galaxy's shining heart. Still, Not everyone agrees on this structure. Some astronomers have suggested that Andromeda might have only a single spiral arm, while others think its arms could be part of a flocculent pattern, a fluffy, irregular web of long, thick filaments rather than smooth, well-defined curves. Much of the distortion in Andromeda's spiral pattern is believed to be caused by gravitational interactions with its smaller companion galaxies, Messier 32 and Messier 110. This influence is visible in the strange displacement of neutral hydrogen clouds, which appear to drift away from the pattern of the galaxy's stars, as if tugged by invisible cosmic hands. In the year 1998, the European Space Agency's Infrared Space Observatory provided a surprising new view of Andromeda. It showed that the galaxy's overall form might actually be changing, gradually transforming into what astronomers call a ring galaxy. Instead of having a smooth spiral structure, its gas and dust appeared to arrange themselves into several overlapping rings. One ring in particular stood out, forming a magnificent circle about 32,000 light-years, or 9.8 kiloparsecs from the galaxy's glowing core. This enormous feature earned a poetic nickname, the Ring of Fire. Hidden from visible light by cold interstellar dust, this region glows brightly in infrared images, revealing that it is one of the most active zones of star formation in the entire galaxy. Later observations with the National Aeronautics and Space Administration's Spitzer Space Telescope offered an even clearer look. The infrared view showed that Andromeda's spiral structure actually consists of two main arms that spiral outward from a central bar and extend far beyond the large outer ring. Yet these arms are not smooth and continuous. They appear broken and segmented, as if the galaxy's majestic design had been disrupted by past encounters. Closer examination of Andromeda's inner regions with the same telescope revealed a smaller dust ring. Astronomers believe this inner ring was created when the small satellite galaxy Messier 32 passed directly through Andromeda's disk more than 200 million years ago. Computer simulations suggest that this collision occurred along Andromeda's polar axis and stripped away more than half of Messier 32's mass. The violent event also triggered the formation of the concentric rings that now define much of Andromeda's structure. The presence of both a large ancient outer ring and this newly discovered smaller inner ring, slightly offset from the galaxy's centre, strongly supports the idea that Andromeda once experienced a nearly head-on collision with its companion, though less catastrophic than the dramatic encounter that formed the famous Cartwheel Galaxy. Studies of Andromeda's vast outer halo show that it is similar to that of our own Milky Way. The stars in this region are mostly old and metal-poor, meaning they contain fewer heavy elements than younger stars, and their metallicity decreases the farther they lie from the galactic centre. This similarity between Andromeda and the Milky Way suggests that the two galaxies have evolved along comparable paths, each growing by absorbing smaller galaxies. It is believed that both have merged with or consumed between 100 and 200 low-mass galaxies over the past 12 billion years. The halos of both galaxies stretch so far that the outermost stars may reach nearly 1/3 of the distance between the Milky Way and Andromeda themselves, a vast invisible bridge of ancient starlight. At the very core of the Andromeda Galaxy lies a dense, compact cluster of stars, remarkably similar to the one found in the centre of our Milky Way. When viewed through a large telescope, this bright central region appears as a star-like point, shining within a softer, hazy bulge of light. In the year 1991, the Hubble Space Telescope captured a detailed image of Andromeda's inner nucleus, revealing that it actually contains two distinct bright regions. These twin concentrations are separated by about 1.5 parsecs, or roughly 5 light-years. The brighter area, known as P1, lies slightly off-centre, while the dimmer one, called P2, marks the true heart of the galaxy. Within P2 resides a compact star cluster called P3, filled with brilliant ultraviolet blue A-type stars and at its very core the galaxy's supermassive black hole, designated Messier 31 star. This colossal black hole is classified as a low-luminosity active galactic nucleus, meaning it feeds quietly on surrounding matter and emits mostly radio and X-ray radiation. It remained mostly inactive between the years 2004 and 2005, but displayed dramatic outbursts between 2006 and 2007, followed by another X-ray flare in the year 2013. Earlier measurements in 1993 estimated its mass to be between 30 and 50 million times that of our Sun, while later observations in 2005 placed it between 110 million and 230 million solar masses. The material swirling around it moves at astonishing speeds of about 100 miles per second, showing the immense gravitational power of this hidden giant. Astronomers have proposed that the strange double nucleus of Andromeda might be explained by the presence of a disk of stars orbiting the central black hole in a stretched or eccentric path. In such orbits, stars spend more time at their farthest points, creating a concentration of light that makes one side appear brighter. This eccentric disk could have formed after a past merger between black holes when the release of gravitational waves violently rearranged the surrounding stars into their current orbits. Within P2, there also exists a compact disk of hot A-type stars that dominate the region's appearance in blue and ultraviolet light, making P2 shine more vividly than P1 when seen through certain filters. When this curious double nucleus was first discovered, some astronomers thought the brighter region might be the remnant of a small galaxy that had been devoured by Andromeda. However, this theory is no longer accepted, since such a nucleus would not have survived long against the intense tidal forces of the central black hole. While it might be possible for P1 to have its own small black hole providing stability, the distribution of stars does not support this idea. Instead, the twin cores of Andromeda's heart stand as evidence of a far more complex and fascinating history, one shaped by ancient collisions, gravitational dances, and the relentless pull of the galaxy's central black hole. By the late part of the year 1968, astronomers had still not detected any X-rays coming from the Andromeda galaxy. Then, on the 20th day of October in the year 1970, a high-altitude balloon experiment set an upper limit for how strong any hard X-rays from Andromeda could be. Years later, the Swift Burst Alert telescope, during its all-sky survey, finally detected hard X-rays coming from a small region about 6 arcseconds away from the galaxy's center. Further study showed that the X-rays coming from energies above 25 kilo electron volts were being emitted by a single source known as 3XMM-J 004232.1 plus 4 11314. This source turned out to be a binary system, where a dense compact object, either a neutron star or a black hole, was pulling in and devouring matter from a nearby star, releasing enormous energy in the process. Since then, astronomers using the European Space Agency's orbiting observatory, XMM Newton, have discovered many more X-ray sources scattered throughout Andromeda. According to Robin Barnard and his colleagues, these mysterious objects are most likely black holes or neutron stars. As they swallow nearby gas, they heat it to millions of degrees, making it shine brightly in X-rays. The two can be told apart mainly by measuring their masses, black holes being far heavier. Later, the New Star space mission identified 40 such objects within Andromeda, revealing a bustling population of compact energetic systems. In the year 2012, scientists observed something even more extraordinary. A microquasar, a smaller version of a quasar powered by a black hole giving off powerful radio bursts. This tiny black hole, located near Andromeda's galactic center, had about 10 times the mass of our Sun. It was first noticed through data gathered by XMM Newton and later confirmed by NASA's Swift Gamma Ray Burst mission, the Chandra X-ray Observatory, the Very Large Array, and the Very Long Baseline Array. This marked the first time such a microquasar had ever been detected not only within Andromeda, but also beyond our own Milky Way. Andromeda also hosts a great number of globular clusters, dense, spherical gatherings of ancient stars. Around 460 of these clusters are associated with the galaxy. The most massive one, called Male 2 or Globular 1, outshines every other globular cluster in the entire local group of galaxies. Containing several million stars, it is about twice as luminous as Omega Centauri, the brightest globular cluster in the Milky Way. Interestingly, Male 2 has multiple generations of stars and a structure far too massive for an ordinary cluster, leading astronomers to suspect that it might actually be the surviving core of a small galaxy that Andromeda swallowed long ago. The brightest cluster seen from Earth is known as G76, located along the eastern half of Andromeda's southwestern arm. Another enormous cluster, 037 B327 or Bol 37, discovered in the year 2006, was once thought to be even more massive than Male 2, but later studies showed that it shares similar characteristics instead of surpassing it. Unlike the Milky Way's globular clusters, which are all very old, Andromedas show a wide range of ages. Some are as ancient as the galaxy itself, while others are relatively young, only a few 100 million to about 5 billion years old. In the year 2005, astronomers identified a completely new kind of star cluster within Andromeda. These newly found clusters contain hundreds of thousands of stars, similar to globular clusters in number, but they are far larger, stretching several hundred light-years across. Because of their great size, they are also much less dense, with far more space separating each star from the next. The most massive globular cluster in Andromeda, known as B023G078, is believed to contain an intermediate mass black hole at its centre, one that weighs nearly 100,000 times the mass of the Sun. In the year 1999, astronomers witnessed an intriguing microlensing event in Andromeda, known as PA99N2. This event was caused by the gravitational bending of light from a distant red giant star, possibly by another star with a mass somewhere between 2/100ths and 3 6/10ths that of the Sun. The data even hinted that this lensing star might be orbited by a planet roughly 6 1/3 times the mass of Jupiter. If proven true, it would represent the very first planet ever discovered beyond our galaxy, an extragalactic world. However, later analysis revealed some irregularities in the data, leaving the discovery uncertain. Andromeda, much like the Milky Way, has its own system of smaller companion galaxies, more than 20 dwarf galaxies that orbit it. The best known among them are Messier 32, M32, and Messier 110, M110. Evidence suggests that M32 once had a close encounter with Andromeda, perhaps once being a larger galaxy before Andromeda stripped away its outer layers. This event likely triggered a burst of star formation in M32's core that lasted until relatively recent times. M110 too appears to be interacting with Andromeda. Astronomers have detected streams of metal-rich stars in Andromeda's halo that were probably torn away from these smaller companions. 110 contains a dark, dusty lane that hints at ongoing or recent star formation, while M32 hosts a younger population of stars as well. The Triangulum Galaxy, another nearby member of our galactic neighbourhood, lies about 750,000 light-years from Andromeda. It is still unclear whether Triangulum is a satellite of Andromeda, or simply a close neighbour moving independently. In the year 2006, astronomers made a fascinating discovery. 9 of Andromeda's satellite galaxies appear to be aligned in a single vast plane that passes directly through Andromeda's core. This strange and orderly arrangement suggests that these galaxies may share a common tidal origin, perhaps formed or drawn together long ago through the powerful gravitational forces of Andromeda itself. The Andromeda Galaxy, our Milky Way's grand and distant neighbour, is slowly but surely moving toward us at a breathtaking speed of about 110 kilometres, or roughly 68 miles every single second. When its motion is measured relative to the Sun, it appears to be approaching even faster, around 300 kilometres, or 190 miles per second. This difference is because the Sun itself is not still. It moves around the Milky Way's centre at a speed of roughly 225 kilometres, or about 140 miles per second. Because of this motion, astronomers have discovered that the Andromeda Galaxy is one of only about 100 galaxies that are blue-shifted, meaning their light waves are squeezed as they move toward us, creating a faint bluish tint when observed through powerful instruments. However, while its approach is well measured, the galaxy's sideways or tangential motion in relation to our own is less certain. Scientists believe that this sideways motion is slower than the forward approach. When astronomers first measured this sideways movement, they predicted that the Andromeda Galaxy and our Milky Way would collide head-on in roughly 4 billion years. Later, with improved data from the Gaia spacecraft, and a better understanding of the gravitational influences of nearby galaxies in our local group, this prediction was revised. The new findings suggest that while the two galaxies may still interact, the chance of a direct and catastrophic collision is smaller than once believed. If such a cosmic meeting were to occur, the result would likely be spectacular. The two giant spirals might merge into one enormous elliptical galaxy, or perhaps form a vast, bright disc-shaped galaxy unlike anything seen before. Such galactic mergers are not rare. They happen quite often in tightly bound galaxy groups throughout the universe. Yet the ultimate fate of Earth and our solar system during this potential encounter remains a mystery. Some scientists suggest that before the final merger, the gravitational forces could fling our solar system out of the Milky Way entirely, sending it drifting into the endless dark of intergalactic space, or perhaps capturing it within the Andromeda Galaxy itself. From Earth, the Andromeda Galaxy holds a special place in the night sky. It is one of the most distant objects visible to the unaided human eye, a faint misty patch of light hanging in the darkness. Only a few other galaxies, such as the Triangulum Galaxy, known as M33, and, for those with exceptionally sharp vision, the great galaxy M81, can be glimpsed without a telescope under perfectly dark skies. The Andromeda Galaxy lies within the constellation of Andromeda, which is easiest to find by using the nearby constellations Cassiopeia, with its distinctive W shape, or Pegasus, marked by its large square pattern. For skywatchers in the Northern Hemisphere, Andromeda is best observed on crisp autumn nights, when it rises high overhead and shines brightest around midnight in October. With each passing month, it appears a little earlier, about 2 hours sooner each time. By September it can be seen rising in the east during early evening, and by February it sets in the west before midnight. From the Southern Hemisphere, the galaxy can be spotted between the months of October and December, though it appears lower in the sky and is best viewed from regions closer to the equator. Even a simple pair of binoculars can reveal the galaxy's elongated shape and its two brightest companion galaxies, M32 and M110. A small amateur telescope can uncover even more wonders: the hazy glow of Andromeda's enormous disk, its dark dust lanes, a few glittering globular clusters, and a large radiant star cloud known as NGC 206. The Triangulum Galaxy is a stunning spiral-shaped galaxy that lies about 2,730,000 light-years away from Earth, within the small constellation known as Triangulum. Astronomers often refer to it as Messier 33 or NGC 598. When measured across its visible span, known as its D25 isophotal diameter, it stretches roughly 18.74 kiloparsecs, or about 61,100 light-years wide. This makes it the third largest member of our cosmic neighbourhood, the local group of galaxies, after the enormous Andromeda Galaxy and our own Milky Way. Despite its impressive size, the Triangulum Galaxy is actually the second smallest spiral galaxy in the local group, coming just after the Large Magellanic Cloud, which belongs to a smaller class of spirals known as Magellanic-type galaxies. Many astronomers believe that Triangulum might be a companion or satellite galaxy of Andromeda, or perhaps it is now moving back toward Andromeda after having once been closer. This idea comes from their similar velocities and the closeness of their positions in the sky. Interestingly, Triangulum also possesses what is called an H2 nucleus, a region filled with ionized hydrogen gas where new stars are being born. The galaxy's name comes from its home constellation Triangulum, which means triangle. Some astronomy sources have also given it the nickname Pinwheel Galaxy. However, this name is more correctly used for another galaxy, Messier 101, which lies in the constellation Ursa Major. Still, the informal nickname occasionally appears in certain telescope software and astronomy websites, showing how easily confusion can arise between celestial names. Under exceptionally clear and dark skies far from the glare of city lights, the Triangulum Galaxy can sometimes be seen with the naked eye. For those lucky enough to spot it, this faint misty patch of light represents the most distant permanent object visible to unaided human sight, nearly 1.5 times farther away than the Andromeda Galaxy itself. Unlike stars, which appear as sharp points of light, Triangulum looks like a soft hazy cloud because of its wide and extended shape. Its visibility depends strongly on how dark and clear the sky is. In deep rural areas with no light pollution, some people can see it directly, while others might only detect it by looking slightly to the side, a technique known as averted vision. Because of this, it is often used as a reference on the Bortle dark sky scale, a system used to measure the darkness of the night sky. Although its total apparent brightness, its so-called V magnitude, is about 5.72, its effective visual brightness is closer to 6.6. This means that only observers with extremely sharp vision and excellent sky conditions can see it without a telescope. For many people, even under the best skies, it remains invisible to the naked eye. The Triangulum Galaxy has a rich history of discovery. It was probably first spotted before the year 1654 by the Italian astronomer Giovanni Battista Hodierna, who described it as a cloud-like spot near the constellation Triangulum. Over a century later, on the night between August 25th and 26th in the year 1764, the French astronomer Charles Messier independently rediscovered it. He recorded it as the 33rd object in his famous catalogue of nebulae and star clusters, hence its name, Messier 33. The great astronomer William Herschel later added it to his own catalogue on September 11th, 1784, calling it HV17. Herschel also studied several glowing clouds of gas within Triangulum, known as H2 regions where young stars are forming. One of these, called NGC 604, lies to the northeast of the galaxy's bright core and is one of the largest H2 regions known. It stretches about 1,500 light-years across, an immense region with a glowing spectrum much like that of the famous Orion Nebula. Herschel also documented 3 smaller neighbouring H2 regions, catalogued as NGC 588, 592 and 595. In the mid-19th century, around the year 1850, Lord Rosse was among the first to identify Triangulum as a spiral nebula, recognising its graceful swirling structure. Then, during the early 1920s, astronomers John Charles Duncan and Max Wolf discovered variable stars within it. In 1926, Edwin Hubble studied 35 of these stars, known as Cepheid variables, and used them to measure Triangulum's distance. His results helped confirm that spiral nebulae like Triangulum were not just clouds within our Milky Way, but were in fact separate galaxies, vast star systems of their own. The Triangulum Galaxy is estimated to contain about 40 billion stars, far fewer than the Milky Way's 400 billion, and tiny compared to Andromeda's trillion stars. Its disk holds between 3 and 6 billion times the mass of our Sun, while its gas content alone amounts to about 3.2 billion solar masses. In total, the galaxy's ordinary or baryonic matter may weigh around 10 billion solar masses. Yet when dark matter is included, its total mass reaches nearly 50 billion solar masses, within a radius of about 55,000 light-years. Astronomers have made many careful attempts to measure how far Triangulum is from us. The most common estimates place it between 2,380,000 and 3,070,000 light-years away, with most agreeing on a middle value of about 2,770,000 light-years. This makes it slightly more distant than Andromeda. Triangulum is also about 750,000 light-years away from Andromeda, which supports the idea that the two galaxies may be gravitationally connected. In the year 2006, astronomers discovered an eclipsing binary star system within Triangulum. By studying how one star passed in front of the other, they could determine their sizes, brightness, and true distance, about 3,070,000 light-years from Earth. This confirmed earlier estimates and provided one of the most precise distance measurements ever made for a nearby galaxy. The Triangulum Galaxy also emits a special kind of radiation known as a water maser signal, which allows astronomers to measure its motion through space. Using this method in 2005, scientists found that Triangulum is moving toward the Andromeda Galaxy at a speed of roughly 190 kilometers per second. This supports the theory that it might be orbiting Andromeda or heading back toward it after a past encounter. Further studies in the early 21st century revealed a faint stream of hydrogen gas linking the two galaxies, suggesting that they may have interacted long ago. Later observations confirmed this connection, showing that their separation of less than 300 kiloparsecs, about 1 million light-years, makes such an interaction highly likely. Nearby lies a small galaxy known as the Pisces Dwarf, or LGS-3. It sits about 2,022,000 light-years from the Sun, and lies roughly midway between Andromeda and Triangulum. Because it is about 913,000 light-years from both, it could be a tiny satellite of either one. It contains around 26 million solar masses of material and has a core roughly 483 light-years wide. Another small object called Pisces 7, or Triangulum 3, may also be a faint companion of the Triangulum Galaxy. In the revised Hubble Sandage system of galaxy classification, created by the French astronomer Gérard de Vaucouleurs, the Triangulum Galaxy is listed as type SA-S.CD. Each part of this label tells astronomers something special about its shape and structure. The letter S means that the Triangulum Galaxy has a flat disc-like form with striking arms of gas and dust spiralling out from its glowing centre. the familiar structure that defines a spiral galaxy. The letter A indicates that its nucleus does not have a bar-like structure running through it, unlike galaxies of the SB type, which do contain a distinct bar. The notation S, introduced by the American astronomer Alan Sandage, shows that the spiral arms emerge directly from the central nucleus, instead of springing out from a surrounding ring. Finally, the CD at the end marks where the galaxy stands along the spiral sequence. Galaxies with C or D classifications have loosely wound, open spiral arms, which gives them a more graceful, delicate appearance. The Triangulum Galaxy lies tilted at an angle of about 54 degrees from our line of sight on Earth. This tilt is fortunate because it allows astronomers to look at its disk and spiral arms without too much interference from its clouds of gas and dust. When scientists carefully mapped the shape of the galaxy's disk, they noticed that it bends or warps slightly outward, extending to a distance of about 8 kiloparsecs from the centre, roughly 26,000 light-years. Although there might be a faint halo of stars and gas encircling it, the Triangulum Galaxy does not appear to have a dense, bulging core at its centre, unlike many other spiral galaxies. Interestingly, the Triangulum Galaxy lives a rather solitary life. It shows no signs of having recently collided or merged with other galaxies, nor does it display the faint star trails or small companion dwarf galaxies that are found around our Milky Way. It is officially described as an unbarred spiral galaxy, yet closer examination suggests that a faint short bar-like feature may exist near its nucleus. This weak structure stretches out to a radius of about 0.8 kiloparsecs, a little over 2,500 light-years, suggesting that even in an unbarred galaxy, some subtle bar patterns can still appear. In the galaxy's central region, which spans about 4 arc-minutes across the sky, a fascinating process is taking place. Here, clouds of atomic gas are efficiently turning into molecular gas, producing strong emissions of carbon monoxide, a clear sign of active molecular formation. This transformation happens as immense molecular clouds condense out of the interstellar medium that fills the space between stars. Beyond this central region, the same process continues but at a much slower rate. Altogether, about 1/10 of all the gas in the Triangulum Galaxy exists in molecular form, the key ingredient for the birth of new stars. Star formation in Triangulum follows a clear and beautiful pattern. The denser the gas in a region, the faster new stars are born there. In fact, the rate of star formation per unit area is higher here than in the neighbouring Andromeda Galaxy. For every square parsec of its disk, Triangulum creates stars at an average rate of about 3.4 solar masses per billion years, compared to only about 0.74 in Andromeda. Altogether, the entire galaxy produces about 0.45 solar masses of new stars each year, although astronomers are still unsure whether this rate is holding steady or gradually slowing down over time. When researchers studied the chemical makeup of the Triangulum Galaxy, they discovered that it seems to consist of 2 main parts, each with a different evolutionary story. The inner disk, stretching about 30,000 light-years, or 9 kiloparsecs from the core, shows a typical gradient in its chemical composition. The concentration of heavy elements steadily decreases as one moves outward from the centre. Beyond this region, extending out to about 82,000 light-years, or 25 kiloparsecs, this gradient becomes much flatter. This suggests that the outer disk and halo have had a different history of star formation than the inner regions. Many astronomers believe that this pattern supports what is known as the inside-out model of galaxy growth. In such a process, a galaxy first forms its dense inner regions, where stars rapidly consume much of the available gas. Over time, new gas is gradually drawn in from the surrounding space, gathering in the outer parts and triggering later waves of star formation. As a result, the stars farther from the galaxy's centre tend to be younger on average than those at the core, painting a quiet but elegant story of how the Triangulum Galaxy has slowly built itself outward through cosmic time. By the year 2007, astronomers using the powerful infrared eyes of the Spitzer Space Telescope had catalogued a total of 515 distinct sources of 24 micrometer radiation shining within the Triangulum Galaxy. These glowing spots represent regions rich in dust and gas, often heated by nearby young stars. The brightest of these sources are found in the heart of the galaxy and stretched elegantly along its spiral arms, where new stars are being born in abundance. Many of these glowing clouds are connected with vast H2 regions, enormous clouds of ionized hydrogen where stars are actively forming. Among the most spectacular of these are four immense regions known as NGC 588, NGC 592, NGC 595 and NGC 604. Each of these regions contains colossal molecular clouds weighing between 120,000 and 400,000 times the mass of our Sun. The largest and brightest among them, NGC 604, appears to have experienced a dramatic burst of star formation around 3 million years ago. This magnificent nebula shines with a brightness 45 million times greater than the Sun, making it the second most luminous H2 region in the entire local group of galaxies. Other notable star-forming nebulae scattered throughout the Triangulum Galaxy include IC 132, IC 133, and IK 53. The galaxy's northern spiral arm holds four large H2 regions, while its southern arm is teeming with clusters of young, brilliant, and extremely hot stars. The Triangulum Galaxy also witnesses the occasional cosmic fireworks of dying stars. Astronomers estimate that, on average, one supernova occurs roughly every 147 years, equivalent to about 0.06 type Ia and 0.62 type Ib or type II explosions per century. By the year 2008, scientists had identified about 100 supernova remnants scattered across the galaxy, with most of them lying in its southern half. This uneven distribution extends to other features as well, such as neutral and ionized hydrogen clouds and groups of massive O-type stars. The center of these features appears to be shifted slightly, about 2 arc-minutes, toward the southwest. Because the Triangulum Galaxy is one of our closest galactic neighbors, the Central Bureau for Astronomical Telegrams continues to monitor it closely for new novae, along with the Andromeda Galaxy and Messier 81. Astronomers have also discovered about 54 globular clusters orbiting within the Triangulum Galaxy, though the true number could be as high as 122 or more. Interestingly, these clusters seem to be several billion years younger than those found in our own Milky Way, suggesting that the galaxy has continued forming new clusters relatively recently. In fact, over the past 100 million years, the rate of cluster formation appears to have increased, likely due to an inflow of gas toward the galaxy's center. The ultraviolet glow from its massive stars matches that seen in similar stars of the Large Magellanic Cloud, showing that the Triangulum Galaxy remains a lively and active place of starbirth. In the same year, 2007, astronomers made another remarkable discovery using data from the Chandra X-ray Observatory, a black hole about 15.7 times the mass of our Sun, named M33X7. This stellar black hole orbits a companion star, passing directly in front of it every 3.5 days, creating a regular eclipse. It remains one of the largest stellar mass black holes ever detected. Unlike our Milky Way and the majestic Andromeda Galaxy, the Triangulum Galaxy does not appear to possess a supermassive black hole at its center. This is likely because such enormous black holes are usually found within galaxies that have a large central bulge, a feature that the Triangulum lacks, since it is a pure disk galaxy without any central swelling. Observations have also revealed that the Triangulum Galaxy is connected to the Andromeda Galaxy through delicate bridges of neutral hydrogen gas and streams of stars. These faint connections suggest that the two galaxies may have interacted billions of years ago, possibly between 2 and 8 billion years in the past. Astronomers believe that in about 2.5 billion years, a far more intense encounter between the two will occur. By the year 2009, the future of the Triangulum Galaxy remained uncertain. Some scientists proposed that it might eventually be torn apart and absorbed by the larger Andromeda Galaxy, providing it with fresh hydrogen to form new stars. Others suggested that it might gradually use up all its gas and fade into cosmic quietness. Another possible fate is that it could join the dramatic collision between the Milky Way and Andromeda, eventually becoming part of the massive merged galaxy that will result. There is also a chance, though small, that it could collide with the Milky Way first, or even be flung out of the local group entirely. However, in the year 2019, precise astrometric data from the Gaia Space Observatory revealed new clues. These measurements indicated that the Triangulum Galaxy is not orbiting the Andromeda Galaxy as once thought, but is instead plunging inward for the first time. If this is true, we are witnessing the beginning of its long and complex journey toward a cosmic reunion with Andromeda. The Virgo Cluster is a gigantic family of galaxies gathered together in the part of the sky known as the Virgo constellation. Its centre lies about 53.8 million light-years away from Earth, give or take a few 100,000 light-years. Altogether, this enormous cluster holds roughly 1,300 galaxies, and some scientists believe the total number might be closer to 2,000. The Virgo Cluster forms the heart of an even larger cosmic structure called the Virgo Supercluster, which also includes our own local group, the small neighbourhood of galaxies that contains the Milky Way. The pull of gravity from the Virgo supercluster actually influences the movement of our local group in what astronomers call the Virgocentric flow. It is estimated that the Virgo cluster has a mass equal to about 1.2 quadrillion times the mass of our Sun, spreading across a region about 2.2 million parsecs wide. Many of its brightest galaxies, including the giant elliptical galaxy Messier 87, were first spotted during the late 1770s and early 1780s. These discoveries were later added to Charles Messier's famous catalogue of fuzzy celestial objects that he described as nebulae without stars. At that time, no one yet realized that these glowing patches were not clouds of gas, but entire galaxies far beyond our own. It wasn't until the 1920s that astronomers finally understood their true nature. The Virgo cluster stretches across about 8 degrees of the sky, centered in the Virgo constellation. Some of its more luminous members can be seen with a pair of binoculars or a small telescope, while a telescope with a 6-inch mirror can reveal as many as 160 galaxies on a clear, dark night. The brightest galaxy in the cluster is Messier 49, a majestic elliptical galaxy. The cluster is a diverse mix of both spiral and elliptical galaxies. Observations made around the year 2004 suggest that the spiral galaxies are arranged in an elongated filament that is about 4 times longer than it is wide, stretching along our line of sight from the Milky Way. In contrast, the elliptical galaxies are more densely packed near the cluster's centre. Astronomers have discovered that the Virgo cluster is actually made up of at least 3 main groups or sub-clumps. The first and largest, called Virgo A, is centred on Messier 87. The second surrounds the galaxy Messier 86, and the third, known as Virgo B, is centred on Messier 49. Some researchers also recognise a fourth group, Virgo C, around the galaxy Messier 60, and an additional smaller collection called the Low Velocity Cloud, centred on the large spiral galaxy NGC 4216. Among all these subgroups, Virgo A dominates. Its mass, about 100 trillion times that of the Sun, is roughly 10 times greater than either of the other 2 main groups. It contains a mixture of elliptical, lenticular, and spiral galaxies that tend to have little gas left in them. The 3 main subclusters are currently merging together, forming a larger and more unified cluster. Around them are smaller clouds of galaxies, such as the N cloud, S cloud, and Virgo E cloud, mostly made up of spiral galaxies that are being drawn inward by gravity. Even more distant clouds, like the Coma I group, are also being pulled toward Virgo and are expected to merge with it someday. This process shows that the Virgo cluster is still young in cosmic terms and continues to grow and evolve. Nearby groups of galaxies known as the M cloud, W cloud, and W prime cloud appear to be separate background systems, lying farther away and not directly part of the main Virgo cluster. The massive weight of the cluster reveals itself through the extremely high speeds of many of its galaxies, some racing at up to 1,600 km per second relative to the cluster's centre. Because the Virgo cluster lies within the Virgo supercluster, its powerful gravity affects the motion of galaxies around it. In fact, the cluster's enormous mass slightly slows down the outward movement of our own local group, reducing its recession speed by about 10%. One of the most fascinating discoveries about the Virgo cluster is that its galaxies seem to have been swept clean. A kind of cosmic broom has cleared away much of their molecular gas, preventing many of them from forming new stars. Scientists believe this mysterious effect happens because of the harsh and turbulent environment inside the cluster. As with many rich clusters of galaxies, the space between the galaxies, the intracluster medium, is filled with extremely hot thin plasma, reaching temperatures of around 30 million degrees Kelvin. This hot gas glows brightly in X-rays. Floating within this space are countless intergalactic stars, perhaps as many as 1 in every 10 stars in the cluster, that have been thrown out of their home galaxies during close encounters. Among them are even some planetary nebulae and numerous globular clusters that may have been stripped away from smaller dwarf galaxies. Astronomers have even discovered at least one region within this vast expanse where new stars are still being born. The speed of light in a vacuum is one of the most important and unchanging constants in the entire universe. It has a precise value of 299,792,458 meters per second. To put that in perspective, this is roughly equal to 1 billion kilometers per hour, or about 700 million miles per hour, a truly unimaginable speed. This value is exact because, by international agreement, 1 meter is defined as the distance that light travels in a vacuum during 1 divided by 299,792,458 of a second. In other words, our very definition of the meter depends on how fast light moves. What makes this speed so extraordinary is that it is always the same, no matter who measures it, where they are, or how fast they are moving. The speed of a light represents the ultimate cosmic speed limit. Nothing, not matter, not energy, not even information itself, can travel faster than this through space. Every kind of electromagnetic radiation, whether it is visible light, radio waves, microwaves, X-rays, or gamma rays, travels at this same astonishing speed when in a vacuum. In everyday life, light seems to move instantaneously. When we switch on a lamp, the room lights up instantly, giving the impression that light has no delay. But when distances grow vast, such as those between stars and galaxies, the finite speed of light becomes noticeable. The starlight we see at night, for instance, has taken years, centuries, or even millions of years to reach us. That means when we look up at the sky, we are actually looking back in time, seeing stars and galaxies as they were long ago. Similarly, when scientists communicate with distant spacecraft, their signals can take many hours to arrive. Even in modern computers, the speed of light sets an unavoidable limit on how quickly information can be transmitted. Using this constant, scientists can also measure enormous distances with incredible accuracy through a method known as time-of-flight measurement. The story of how humanity discovered that light does not move instantaneously began in the 17th century. The Danish astronomer Ole Rømer was the first to show that light had a finite speed. He noticed small delays in the observed motion of Jupiter's moon Io, and realized that these delays were caused by the changing distance between Earth and Jupiter, as light took time to travel the extra distance. Much later, in the year 1865, the Scottish physicist James Clerk Maxwell proposed that light was actually an electromagnetic wave, a ripple in electric and magnetic fields, and that it must travel at speed c. 4 decades after Maxwell, in the year 1905, Albert Einstein took this concept even further. In his theory of special relativity, he proposed that the speed of light is constant for all observers, regardless of their motion or the motion of the source of the light. From this simple but powerful idea, Einstein built an entirely new understanding of space and time, showing that c connects them in ways that were previously unimaginable. He also revealed that this constant plays a key role in his famous equation, E mc2, which links mass and energy together. Only massless particles, such as photons, the particles of light, and gravitational waves can move at the speed of light. Anything that has mass can only approach this speed, but can never actually reach it, no matter how much energy it gains. In relativity, as an object moves faster and faster, its energy and momentum increase dramatically, making it impossible to accelerate it beyond the speed of light. Sometimes, things in the universe appear to move faster than light, but this is usually an illusion. For instance, the fabric of the universe itself, space-time, can expand faster than light, as seen in the distant galaxies racing away due to cosmic expansion. However, the objects within space are not breaking the universal speed limit. Rather, space itself is stretching. Light also slows down when it passes through materials such as glass or air. In such cases, scientists describe how much slower it travels using something called the refractive index, represented by n. This value is the ratio of c to the speed of light v in the material. For visible light, glass typically has a refractive index of about 1.5, meaning that light travels through it at roughly 200,000 kilometers per second, or about 124,000 miles per second. Air, by comparison, has a refractive index of about 1.0003, so light in air is only about 90 km per second slower than in a vacuum. The origin of the letter C to represent the speed of light is somewhat mysterious. Some believe it stands for the Latin word celeritas, meaning swiftness or speed. The great mathematician Leonhard Euler and others used the letter C for general velocity in earlier works, though not specifically for light. In the mid-19th century, physicists Wilhelm Eduard Weber and Rudolf Kohlrausch used C for a constant later shown to be equal to the square root of 2 times the speed of light. James Clerk Maxwell, in his writings of 1865, sometimes used the letter V instead. By the early 20th century, however, the symbol C had become standard. Max Abraham popularized it in a textbook in the year 1903, and a few years later, Einstein himself adopted it permanently in his works on relativity. In some scientific writings, C0, that is, C with a subscript 0, is used to mean the speed of light specifically in a vacuum, to distinguish it from light's slower speed in materials. This notation mirrors the way other constants, like the magnetic constant m0 and the electric constant e0, are written. Since the year 1983, the speed of light has been officially fixed by international agreement as exactly 299,792,458 meters per second. This definition was chosen to make the meter itself more precise, defining it as the distance that light travels in a vacuum in 1 divided by 299,792,458 of a second. The second, in turn, is defined using the vibrations of the cesium-133 atom, which oscillates 9,192,631,770 times in a single second. In older unit systems, such as the imperial system, the speed of light is about 186,282 miles per second, which is roughly 1 foot per nanosecond, meaning that light could travel the length of your arm in the blink of an eye and then some. In certain areas of physics, especially those dealing with relativity, scientists often simplify their equations by setting c equal to 1. This makes calculations cleaner and emphasizes that, in nature, the speed of light is not just a number, it is a fundamental link between space, time, energy, and matter. The speed at which light travels through empty space never changes. It remains exactly the same no matter how fast the light source itself is moving or how the observer is moving. This remarkable property of light, that its speed is always constant, was proposed by the German-born physicist Albert Einstein in the year 1905. He was inspired by James Clerk Maxwell's theory of electromagnetism and by the fact that no experiment had ever found any sign of motion through the so-called luminiferous ether, which was once thought to be the invisible substance carrying light waves through space. Later experiments, such as the Kennedy-Thorndike and Ives Stilwell experiments, confirmed that Einstein's idea matched what nature actually does. Einstein's special theory of relativity was built on this amazing discovery, the fact that the speed of light, usually written as c, is the same for everyone no matter how they move. He also assumed that the laws of physics are identical in all steady, non-accelerating frames of reference. From these two simple principles came some of the most mind-bending truths in science. One of them is that c is the ultimate speed limit of the universe, the speed that every massless particle or wave, including light itself, must travel through a vacuum. Special relativity leads to a number of effects that seem impossible at first, but have been proven again and again by experiment. It shows that mass and energy are two sides of the same coin, expressed in the famous equation E just mc2, meaning that even a small amount of mass contains an enormous amount of energy. It also predicts that objects moving close to the speed of light will shrink in length, known as length contraction, will appear visually rotated, terral rotation, and will experience time more slowly, time dilation. The amount by which space shortens and time slows down is described by a number called the Lorentz factor, written as the Greek letter gamma. For everyday speeds, like cars, planes, or even rockets, gauge is almost equal to 1, meaning relativity's effects are so tiny that we never notice them. But as the speed gets closer to that of light, these effects grow dramatically. For example, when something moves at about 86.6% of the speed of light, time slows by a factor of 2, and at 99.5%, time slows by a factor of 10. All these results can be understood by thinking of space and time not as separate things but as part of a single, woven fabric called space-time. The constant c acts as the thread connecting space and time, giving the universe its structure. For a physical theory to work properly, it must obey what is known as Lorentz invariance, a special kind of symmetry that ensures the laws of physics are the same for everyone, no matter how they move. This principle forms the backbone of nearly every modern scientific theory, from quantum electrodynamics and quantum chromodynamics to the standard model of particle physics and Einstein's general theory of relativity. In Einstein's later work on general relativity, c also turns out to be the speed at which gravity itself travels, the speed of gravitational waves that ripple through space-time. Observations of these waves, made over a century later, have confirmed this prediction perfectly. In regions of curved space-time or accelerating reference frames, the local speed of light remains constant and equal to c, but when measured from far away, it can appear to vary depending on how the measurement is made. Scientists generally believe that fundamental constants like c do not change with time or place. They are the same everywhere in the universe and always have been. Yet some speculative theories have suggested that the speed of light might have been slightly different in the distant past. So far, no convincing evidence has been found to support that idea, but researchers continue to test it with ever greater precision. Another remarkable property of light is that its speed is isotropic. It stays the same in every direction. Experiments such as the Hughes-Drever test, which studied how atomic nuclei emit radiation in magnetic fields, and tests involving rotating optical resonators, have shown that if there is any directional difference in the two-way speed of light, it must be unimaginably small. When an object with mass m moves at a speed vs relative to a laboratory, its kinetic energy increases according to the equation. Because the Lorentz factor g grows larger as v approaches c, it would take an infinite amount of energy to accelerate any object with mass to the speed of light. This makes c the absolute speed limit for all matter in the universe. Experiments with individual photons, the smallest packets of light, confirm that information itself cannot move faster than this cosmic limit. Countless tests of relativistic energy and momentum have all agreed, nothing with mass or energy can surpass c. This rule protects what physicists call causality, the natural order of cause and effect. Imagine two events, A and B, that are too far apart in space for even light to travel between them in time. In that case, different observers could disagree on which happened first. Some would see A before B, others would see B before A, and some might see them as simultaneous. If something could move faster than light, it would mean an effect could occur before its cause, breaking the logical flow of time. This would create paradoxes, like sending a message to the past before you even wrote it, something no experiment has ever observed. There are a few rare and theoretical cases such as the Scharnhorst effect, which suggest that under very specific conditions, signals might travel just a tiny bit faster than light, perhaps by 1 part in 10 to the 36th power. However, later analyses have shown that even if such an effect exists, it could never be used to send information faster than light or to violate causality. It is only possible to test and confirm through experiments that the two-way speed of light, that is, when light travels from a source to a mirror and then back again, is the same no matter which frame of reference it is measured from. Scientists cannot directly measure the one-way speed of light. For instance, when light moves from a source to a faraway detector, because this would require perfect synchronization of clocks at both ends. Since no one can synchronize those clocks without first assuming something about how light behaves, the problem becomes circular. To solve this, Albert Einstein proposed a simple rule known as Einstein's synchronization. According to this rule, the one-way speed of light is defined to be the same as its two-way speed. This definition ensures that light always travels at the same constant speed, no matter the direction or the observer's motion. There are, however, situations in which it might seem as though matter, energy, or information can move faster than the speed of light. But these are illusions, not physical realities. For example, when light passes through certain materials such as glass or water, the waves that describe its behavior can have different speeds. The phase velocity of X-rays, which describes how the peaks of the wave move, can even be faster than light. Yet, this does not mean that any information or energy is being transmitted faster than light. It only means the wave's pattern is shifting in a special way that does not carry real information. A simple example can be seen with a laser pointer. If you shine a laser on a faraway wall and quickly move your hand, the bright dot of light can sweep across the surface faster than light itself. But this does not break any physical laws. The laser's photons still travel from your hand to the wall at the constant speed of light. The moving dot is not a real object. It is just a series of light spots appearing one after another in different places. The same is true for a shadow. If a shadow moves across a large distance, it can seem to race faster than light, but nothing physical is actually moving that fast. In both cases, no matter, energy or information is truly travelling faster than light. Another interesting case occurs when two objects are moving toward or away from each other. If both are moving in opposite directions, the rate at which the distance between them changes, known as their closing speed, can be greater than the speed of light. But again, this does not mean either object itself is breaking the universal speed limit. It only means that, from a certain point of view, the distance between them is shrinking faster than light would travel, even though each object is moving slower than light in its own reference frame. In the strange world of quantum physics, some effects appear to happen faster than light. One famous example is the Einstein-Podolsky-Rosen paradox, often called quantum entanglement. When two tiny particles become entangled, their quantum states are linked. If one particle is measured, the other's state becomes known instantly, even if they are far apart. This seems to happen faster than light could travel between them. However, no real information is exchanged in this process, because no one can control which result will appear when the first particle is measured. So, although the effect is instantaneous, it cannot be used to send a message or signal faster than light. Another quantum phenomenon known as the Hartmann effect seems to predict faster than light travel under special conditions. When a virtual particle tunnels through a barrier, an event that happens on the quantum scale, the time it takes to do so appears not to depend on how thick the barrier is. This can make it look as if the particle has crossed the barrier faster than light could have, but once again, this effect cannot carry information, so no physical law is broken. In astronomy, there are also cases where things seem to move faster than light. Certain distant galaxies, quasars and radio sources shoot out long, thin streams of matter called relativistic jets. These jets sometimes appear to be racing across the sky at superluminal or faster than light speeds. However, this is an optical illusion caused by the angle at which they move relative to Earth. The jets are actually moving close to, but not beyond, the speed of light. Because of how their light reaches us, with light from farther points taking longer to arrive, the motion appears exaggerated. In the year 2011, an experiment briefly made headlines when it seemed that tiny particles called neutrinos had travelled faster than light. This caused great excitement and confusion until scientists discovered that the result came from a faulty cable connection and timing error. When corrected, the particle's speed was found to obey the universal limit once again. Even on the grandest scale of all, the universe itself, some things seem to move faster than light. As space expands, distant galaxies drift away from us, and the farther they are, the faster this drift appears to be. Beyond a certain boundary known as the Hubble sphere, galaxies seem to recede from Earth at speeds greater than the speed of light. But this does not mean those galaxies are actually moving through space that fast. Instead, it is the space itself between us and those galaxies that is stretching. These faster-than-light recession speeds are not true motions, but rather a feature of how the universe's geometry changes with time, a cosmic illusion born from the fabric of space-time itself. In the world of classical physics, light is understood as a kind of electromagnetic wave, a rhythm of electric and magnetic fields dancing through space. The way these fields behave was famously described by James Clerk Maxwell in the 1860s through what we now call Maxwell's equations. These equations tell us that light travels in a vacuum at a speed, commonly denoted by the letter c, which depends on two fundamental properties of empty space: the electric constant, often called epsilon zero, and the magnetic constant, called mu zero. In essence, the vacuum itself has a kind of hidden structure that sets the pace for light's journey across the cosmos. As physics advanced into the 20th century, the understanding of light took a more quantum twist. In modern quantum physics, particularly in the theory known as quantum electrodynamics, or QED, light is no longer just a wave, it is also made of particles called photons. These photons are the smallest units, or quanta, of the electromagnetic field. Remarkably, photons have no mass, and according to Einstein's special relativity, any particle without mass must travel at the cosmic speed limit, the speed of light in vacuum. Scientists have explored hypothetical versions of QED in which photons might have a tiny, almost unimaginably small mass. If that were true, the speed of light would depend slightly on its frequency, and the universal speed limit of relativity c would represent the fastest light could ever travel. Rigorous experiments, however, have found no variation of light speed with frequency, which puts incredibly strict limits on any possible photon mass. Depending on the theoretical model, the upper bound for a photon's mass could be as small as around 10 to the negative 57 grams, or, under a Higgs-based model, up to roughly 2 times 10 to the negative 47 grams. These numbers are so tiny they defy ordinary human imagination. Another possible reason for light speed to vary comes from theories suggesting that space and time might behave differently at extremely tiny scales, as predicted by some ideas in quantum gravity. In 2009, astronomers observed a distant gamma-ray burst named GRB 090510 and found no evidence that photons of different energies travelled at different speeds. This observation confirmed that, even at energies approaching the Planck scale, the speed of light remains remarkably constant. In everyday materials, however, light rarely travels at its vacuum speed. Different kinds of light waves can move at different rates depending on the medium. For a simple, single-frequency wave, the speed of its crests and troughs is called the phase velocity. A pulse of light, which has a finite extent, moves at the group velocity, while the very front edge of the pulse travels at the front velocity. Phase velocity is important because it helps us understand how light moves through one material or jumps into another. Scientists often describe this using the refractive index, which is the ratio of the speed of light in vacuum to its speed in the material. A higher refractive index means light slows down more. Air has a refractive index of roughly 1.0003, while denser substances like water, glass and diamond have refractive indices of around 1.3, 1.5 and 2.4, respectively, for visible light. In some exotic substances, such as Bose-Einstein condensates cooled to nearly absolute zero, light can slow to just a few meters per second. This doesn't mean light is fundamentally slower, rather it is repeatedly absorbed and re-emitted by atoms, which creates the illusion of slowness. In extreme experiments, physicists even managed to bring light to a complete standstill in a condensate of rubidium atoms. In reality, the light was temporarily stored in atomic excitations and then released by another laser pulse. During this period, it was no longer light in the conventional sense. This kind of behavior occurs, on a microscopic scale, in all transparent media that appear to slow light. Normally, transparent materials have a refractive index greater than 1, so light travels slower than c. Some unusual materials, however, can have refractive indices smaller than 1 for certain frequencies, and in very exotic cases even negative. The laws of causality ensure that in such materials the speed of light is constrained, linking the material's refractive properties and absorption in a precise mathematical way, known as the Kramers-Kronig relations. When a pulse of light has different group and phase velocities, a situation caused by variations in speed for different frequencies, the pulse spreads out over time, a phenomenon called dispersion. Certain materials can create extraordinarily slow group velocities, a situation called slow light. Conversely, under special conditions, group velocities faster than c can occur, a concept first proposed in 1993 and achieved experimentally in 2000. In theory, group velocity could even appear infinite or negative, making pulses seem to travel instantaneously or even backward in time. Despite all these strange effects, no information can travel faster than the ultimate cosmic speed limit c. The earliest part of a light pulse, the front velocity, always obeys this limit. Particles can sometimes move through a medium faster than light's phase velocity in that medium, though still slower than c. When charged particles do this in certain materials, they produce a kind of electromagnetic shock wave known as Cherenkov radiation, a glowing signature often seen in nuclear reactors or particle detectors. The speed of light plays a crucial role in many areas of technology and science, particularly in communication. Whenever information or signals are sent from one place to another, there is always a small but measurable delay, whether the journey is over a few centimeters or across the vastness of space. This is true whether the signal is traveling in a laboratory, across continents, or between planets. Interestingly, This finite speed of light is not just a limitation, it is also used as a tool in some technologies, such as measuring distances by timing how long light takes to travel. In modern computers, the speed of light sets a hard limit on how fast data can move between different parts of a system. For instance, if a processor operates at 1 GHz, meaning 1 billion cycles per second, a signal can travel at most around 30 centimeters, or roughly 1 foot, during a single clock cycle. In reality, the distance is often shorter, because the circuits on the computer's board slow down the signals slightly due to refraction. This limitation forces engineers to place processors and memory chips very close together and to carefully design the paths that wires follow to maintain signal quality. As processors become faster, the speed of light itself could eventually become a major factor, limiting how a single chip is designed. To put things into a larger perspective, the Earth's equatorial circumference is roughly 40,075 kilometers, and since the speed of light is about 300,000 kilometers per second, the absolute minimum time for information to travel halfway around the Earth along its surface is roughly 67 milliseconds. However, when light travels through optical fibers, which are the thin glass threads that carry the majority of modern communication signals, it moves slower, about 35% slower, because of the fiber's refractive properties. Real-world signal paths are rarely perfectly straight, and the time increases further when signals pass through switches, repeaters, or other electronic equipment along the way. For most applications, this tiny delay is unnoticeable. But in fields such as high-frequency trading, every fraction of a second can make a huge difference. Traders sometimes switch from fiber optics to microwave signals because radio waves travel through air, almost as fast as light in a vacuum, offering them a slight edge in sending transactions faster than competitors. The finite speed of light also affects space exploration. Signals from Earth to spacecraft are never instantaneous. When Apollo 8 became the first human crewed spacecraft to orbit the Moon, every message sent from mission control had to travel over the empty space between the Earth and the Moon, creating a delay of at least 3 seconds before astronauts could respond. For missions to Mars, the delay can range from about 5 to 20 minutes, depending on the relative positions of the two planets. If a robot exploring the Martian surface encounters a problem, humans on Earth would not know about it for several minutes, and any instructions sent to fix the issue would take just as long to reach the robot. Observing the universe pushes this delay to extreme scales. Light from the farthest galaxies captured in the Hubble ultra-deep field images takes around 13 billion years to reach Earth. This means that when we look at these galaxies today, we see them as they existed 13 billion years ago, at a time when the universe was less than 1 billion years old. This remarkable property of light allows astronomers to piece together the history and evolution of stars, galaxies, and the universe itself. Because distances in space are so vast, astronomers often measure them in light years. The distance light travels in 1 Julian year, which is roughly 9,461 billion kilometers, or 5,879 billion miles. In simpler round numbers, a light year is nearly 10 trillion kilometers, or nearly 6 trillion miles. For context, the closest star to Earth beyond the Sun, Proxima Centauri, is about 4.2 light-years away. The speed of light is also the foundation for precise measurements closer to home. Radar systems determine how far away objects are by timing how long a radio wave pulse takes to travel to the target and back. Global Positioning System receivers calculate their positions by measuring how long signals take to arrive from satellites orbiting the Earth. Since light travels roughly 300,000 kilometers, or 186,000 miles, in a single second, these timing measurements need to be extremely precise. Experiments such as lunar laser ranging, radar astronomy, and the Deep Space Network all rely on measuring the round-trip travel time of light to calculate distances to the Moon, planets, and spacecraft. There are many ways to figure out how fast light travels, a value we call c. One approach is simply to measure the speed of light waves as they move, and this can be done using setups both on Earth and far out in space. Another way is more indirect. Light appears in some of the fundamental laws of physics, so by measuring other quantities in those laws, we can calculate the speed of light. For example, light speed can be found using the electric constant and the magnetic constant of the vacuum, which are sometimes called E0 and M0, and applying the formula that connects them to c. Historically, however, The most precise measurements came from measuring the frequency and wavelength of a beam of light separately, because when you multiply these two quantities together, you get the speed of light. This approach is explored in more detail in the section on interferometry. In the year 1983, the definition of a meter was changed in a way that fixed the speed of light. The meter was officially defined as the length of the path travelled by light in a vacuum during a time interval equal to 1/299,792,458 of a second. This means that by definition, the speed of light in vacuum is exactly 299,792,458 meters per second. From that point on, measuring the speed of light precisely no longer gave a more accurate value of c itself. Instead, it became a way to realize or define the length of the meter with great precision. Outer space offers an ideal place to measure light speed because of its vast distances and near-perfect vacuum. Scientists often measure how long it takes light to travel across a known distance in the solar system. For example, the radius of Earth's orbit around the Sun. In the past, these measurements could be made quite accurately compared to how precisely the distances themselves were known in Earth-based units. The first quantitative estimate of light speed was made by the Danish astronomer Ole Rømer in the year 1676. He noticed a curious effect while studying the innermost large moon of Jupiter, called Io. From Earth, the time it took for Io to orbit Jupiter appeared slightly shorter when Earth was moving toward Jupiter and slightly longer when Earth was moving away. The difference was tiny over a single orbit, but after many months it added up to something measurable. Rømer realized that this change in timing occurred because the distance light had to travel from Jupiter to Earth varied depending on Earth's position in its orbit. When Earth was closest to Jupiter, the light had a shorter distance to cover. When Earth was farthest, the distance was longer. By carefully observing Io's orbital timing, Rømer concluded that light takes about 22 minutes to cross the diameter of Earth's orbit. This was the first rough but revolutionary estimate of the speed of light. Another fascinating method involves something called the aberration of light, discovered and explained by the English astronomer James Bradley in the 18th century. This effect happens because light arriving from a distant star combines with the motion of its observer, Earth moving around the Sun, like adding two velocities together. As a result, a moving observer sees the light coming from a slightly shifted direction. Because Earth's velocity constantly changes as it travels along its orbit, this makes stars appear to wobble slightly in the sky. By measuring the maximum angular shift, which is about 20.5 arcseconds, Bradley could relate the speed of light to Earth's orbital speed. Using this method in the year 1729, he estimated that light travels over 10,000 times faster than Earth moves around the Sun, a figure very close to the modern value, and that it would take light approximately 8 minutes and 12 seconds to travel from the Sun to Earth. For a long time, measuring the speed of light also helped determine the astronomical unit, the average distance from Earth to the Sun. In 2012, the astronomical unit was redefined as exactly 149,597,870,700 meters. This redefinition, similar to the 1983 meter definition, effectively fixed the speed of light in astronomical units per second. On Earth, one of the classic ways to measure light speed is to measure the time it takes for light to travel to a mirror and back. This principle was used in famous experiments by the French scientists Hippolyte Fizeau and Léon Foucault. Fizeau's setup involved sending a beam of light toward a mirror 8 kilometers away. On the way, the light passed through a rotating cogwheel. At just the right rotation speed, the light would pass through a gap in the wheel on the way out and another gap on the way back. If the wheel rotated slightly faster or slower, the light would hit a tooth instead and be blocked. By knowing the distance to the mirror, the number of teeth on the wheel, and the wheel's rotation speed, Fizeau could calculate the speed of light. Foucault improved on this method by replacing the cogwheel with a rotating mirror. Because the mirror spins while light travels to the distant mirror and back, the returning light is reflected at a slightly different angle than when it left. Using this difference, the known rotation speed of the mirror, and the distance to the mirror, the speed of light can again be determined. Foucault even used this method to compare the speed of light in air versus water, following a suggestion by the French scientist François Arago. Today, modern technology allows scientists to measure the speed of light even more directly. Using instruments like oscilloscopes, which can record events with time resolutions smaller than 1/1000th of a second. It is possible to time how long it takes a pulse of light from a laser or LED to travel to a mirror and back. While this method is less precise, with errors of around 1%, it is simple enough to be used in physics laboratories as an educational experiment, giving students a hands-on glimpse of one of nature's fastest phenomena. One fascinating way to discover the speed of light, without ever directly timing how fast electromagnetic waves travel, is to rely on a clever relationship uncovered by the brilliant 19th century physicist James Clerk Maxwell. Maxwell revealed that the speed of light, symbolized by the letter c, is intimately connected to two fundamental properties of empty space, known as the vacuum permittivity and the vacuum permeability, represented by the symbols E0 and M0. This relationship is elegantly simple. C squared equals 1 divided by the product of E0 and M0. The vacuum permittivity, E0, can be measured by carefully examining how a capacitor stores electric charge and noting its physical dimensions. Meanwhile, the vacuum permeability, M0, was historically set by definition at the value 4 times pi times 10 to the power of -7 henries per meter, based on how the ampere, the unit of electric current, was defined. Using this approach, in the year 1907, the scientists Rosa and Dorsey calculated the speed of light to be 299,710 km per second, with a possible margin of error of plus or minus 22 km per second. Their calculation relied on the international ohm, a standard unit of electrical resistance, and the accuracy of their result was limited by how precisely that standard was known. Another approach involves measuring an electromagnetic wave's wavelength, L, and its frequency, F in vacuum, then using the formula C equals L times F. One practical method is through a microwave cavity resonator, where microwaves bounce and resonate inside a cavity of precisely known dimensions. By observing the resonance frequencies and knowing the cavity's size, scientists can calculate the wavelength and thus determine the speed of light. In 1946, Louis Essen and A.C. Gordon Smith measured microwave resonance frequencies inside such a cavity with astounding precision, about plus or minus 0.8 micrometers, using gauges carefully calibrated by interferometry. From this, they calculated the speed of light to be 299,792 km per second, with an uncertainty of plus or minus 9 km per second, a far more precise result than earlier optical methods. By 1950, Essen refined this measurement to 299,792.5 km per second, with an uncertainty of plus or minus 3 km per second. Even a simple demonstration of this technique can be performed at home with a microwave oven. Placing a piece of food, such as marshmallows or margarine, inside the oven without the turntable moving, it will heat fastest at the antinodes, points where the microwave's wave amplitude is strongest. The distance between two antinodes corresponds to half the wavelength of the microwaves. Measuring this distance and multiplying the wavelength by the microwave frequency, typically displayed on the oven as 2450 MHz, allows calculation of the speed of light, often with an error of less than 5%. A highly accurate method involves interferometry, where scientists precisely measure the wavelength of electromagnetic radiation. A coherent beam of light, like that from a laser, is split into two paths and recombined. By adjusting the length of one path and observing the resulting interference pattern, the wavelength is determined. Knowing both the wavelength and frequency allows calculation of the speed of light using C equals L times F. Before lasers, coherent radio waves were used, but their long wavelengths limited measurement precision. Using light of shorter wavelengths improved accuracy, though measuring its frequency directly was challenging. To overcome this, scientists developed a technique starting with a low-frequency signal, easily measured with high precision. From this reference, they generated higher frequency signals in stages, eventually linking a laser to an exact frequency. This method, created by a team at the National Bureau of Standards, later the National Institute of Standards and Technology, allowed the speed of light in vacuum to be measured in 1972 with an astonishingly small uncertainty of about 3.5 parts in a billion. For much of human history, people were unsure whether light travelled instantaneously or at a very fast but finite speed. Ancient Greek thinkers, medieval Arabic scholars, and later European scientists debated the nature of light for centuries. It was only in the late 17th century that the Danish astronomer Ole Rømer made the first calculation of light speed. Albert Einstein's theory of special relativity, published in 1905, later established that the speed of light is constant in all frames of reference, and since then, measurements have grown increasingly precise. The Greek philosopher Empedocles, who lived around 490 to 430 years before the Common Era, was the first known thinker to suggest that light moves at a finite speed. He reasoned that light must take time to travel because it is in motion. Aristotle, however, disagreed, claiming that light is a presence rather than a movement. Later thinkers, such as Euclid and Ptolemy, suggested vision occurs because light is emitted from the eye, while Heron of Alexandria argued light travels instantaneously, since distant stars seem to appear immediately upon opening one's eyes. Early Islamic philosophers largely sided with Aristotle, doubting that light has a speed. Yet, in the year 1021, the scholar Alhazen, also known as Ibn al-Haytham, wrote the influential Book of Optics. He argued against the emission theory of vision, supporting the idea that light travels from objects to the eye at a finite speed, and that its speed slows in denser materials. He described light as a kind of substantial matter whose motion takes time, even if imperceptible to the senses. Around the same period, Abu Rayhan al-Bahruni also argued that light has a finite speed, moving far faster than sound. In the 13th century, Roger Bacon followed Alhazen and Aristotle in asserting that light does not travel infinitely fast in air. Later, in the 1270s, Witello proposed that light might move infinitely fast in a vacuum, but slows in denser substances, showing that scientists were already beginning to understand the complex behavior of light. In the early 17th century, the great astronomer Johannes Kepler thought that light must travel infinitely fast because empty space seemed to offer it no resistance at all. Around the same time, the philosopher René Descartes reasoned that if light had a finite speed, then during a lunar eclipse the Sun, Earth and Moon would appear slightly out of alignment. Of course, this idea overlooked a phenomenon called the aberration of light, which would not be discovered until the following century. Since no such misalignment had ever been noticed, Descartes confidently concluded that the speed of light was infinite. He even went so far as to suggest that if one day the speed of light were proven finite, his entire philosophical system might collapse. Yet despite this bold claim, Descartes, in his derivation of Snell's law of refraction, assumed that some sort of motion associated with light actually moved faster in denser materials. In contrast, Pierre de Fermat, another brilliant mathematician, derived Snell's law using the opposite assumption, that the denser the medium, the slower light travelled, and he also argued in favour of a finite speed of light. In 1629, the Dutch scientist Isaac Beeckman suggested a simple experiment. A person could watch the flash of a cannon reflected off a mirror about 1 mile, or 1.6 kilometres, away. A few years later, in 1638, Galileo Galilei proposed a similar experiment, claiming that he had tried it some years earlier. He planned to uncover a lantern and observe the tiny delay before the light was seen at some distance. Unfortunately, the experiment could not detect whether light travel was instantaneous or just extremely fast. Nevertheless, Galileo concluded that even if light were not instantaneous, it must still travel at an astonishing speed. He noted that the lanterns he used were at a short distance, less than a mile. If we take the distance as roughly a mile and remember that the minimum interval the unaided human eye can detect is about 1/30th of a second, modern historians like Boyer estimate that Galileo's experiment could at best have shown that light travels no slower than about 60 miles per second. Later, in 1667, the Accademia del Cimento in Florence reported attempting Galileo's experiment with lanterns separated by roughly 1 mile, yet still no delay was seen. In reality, the actual delay in this setup would have been about 11 microseconds, far too brief to notice without precise instruments. The first real numerical estimate of light speed came in 1676 from the Danish astronomer Ole Rømer. By carefully observing that the periods of Jupiter's innermost moon, Io appeared slightly shorter when Earth was moving toward Jupiter and longer when receding, he realized that light must travel at a finite speed. From this, he calculated that light takes 22 minutes to cross the diameter of Earth's orbit. The Dutch physicist Christian Huygens then used Römer's estimate, along with a calculation of the Earth's orbital diameter, to determine that light travels at about 220,000 kilometers per second, roughly 27% slower than the modern value. In his 1704 book Optics, Isaac Newton discussed Römer's work on light's finite speed and estimated that it takes 7 or 8 minutes for sunlight to reach Earth, compared to the modern value of 8 minutes and 19 seconds. Newton also wondered whether the shadows seen during Römer's observations of eclipses were coloured. Being told they were not, he concluded that all colours of light travel at the same speed. Later, in 1729, James Bradley discovered stellar aberration, a subtle effect caused by Earth's motion. By studying it, he calculated that light travels 10,210 times faster than Earth in its orbit, very close to the modern value of 10,066 times faster, or, equivalently, that sunlight takes about 8 minutes and 12 seconds to reach Earth. In the 19th century, Hippolyte Fizeau developed a method to measure the speed of light on Earth using a time-of-flight experiment, and he reported a speed of 315,000 kilometers per second. Léon Foucault later improved this technique and measured the speed as 298,000 kilometers per second in 1862. In 1856, Wilhelm Eduard Weber and Rudolf Kohlrausch measured the ratio of electromagnetic to electrostatic units of charge by discharging a Leyden jar. Remarkably, this ratio closely matched Fizeau's direct measurements of light's speed. The following year, Gustav Kirchhoff calculated that an electric signal in a wire with no resistance travels at this same speed. In the early 1860s, James Clerk Maxwell showed that, according to his theory of electromagnetism, electromagnetic waves travel through empty space at a speed equal to the Weber and Kohlrausch ratio. Noting that this speed was almost identical to Fizeau's measurement for light, Maxwell proposed the groundbreaking idea that light itself is an electromagnetic wave. He confirmed his theory with experiments published in the Philosophical Transactions in 1868, measuring the ratio of the electrostatic and electromagnetic units of electricity, further strengthening the link between light and electromagnetism. The wave-like behaviour of light had been recognised for a long time, dating back to the experiments of Thomas Young. By the 19th century, many physicists believed that light travelled through an invisible substance called ether, sometimes spelled ether. This idea suggested that light, like sound travelling through air, needed a medium to move through. However, when it came to electric forces, the situation appeared different. Electric forces seemed more like gravity in Newton's theory, which could act at a distance without requiring a medium. When James Clerk Maxwell developed his groundbreaking theory unifying electricity, magnetism and light, the prevailing view became that both light and electromagnetic waves travelled through the same mysterious ether, often called the luminiferous ether. At the time, scientists imagined that empty space was not truly empty, but filled with this ether, which acted as a kind of stage for electromagnetic fields. Some physicists even thought that this ether might provide a preferred frame of reference for light, meaning that if the Earth moved through it, there should be a detectable difference in the speed of light depending on the direction of measurement. Starting in the 1880s, experiments were designed to detect this motion. The most famous of these was the experiment conducted by Albert A. Michelson and Edward W. Morley in 1887. They tried to measure differences in the speed of light as the Earth moved through the ether, but time after time the results showed no motion at all, within the limits of measurement error. Modern experiments confirm this to an astonishing precision, showing that the two-way speed of light is the same in every direction to within 6 nanometers per second. To explain these results, Hendrik Lorentz suggested that an object moving through the ether might physically shrink in the direction of its motion, and that time itself for moving systems would need to be adjusted, a concept he called local time. This led to what became known as the Lorentz transformation. Building on this, Henri Poincaré in 1900 showed that clocks moving through the ether, when synchronized under the assumption that light travels at a constant speed, would measure this local time correctly. He even speculated in 1904 that the speed of light could act as a universal speed limit if Lorentz's assumptions were correct. By 1905, Poincaré had reconciled Lorentz's ether theory with the principle of relativity. In the same year, 1905, Albert Einstein approached the problem differently. He proposed that the speed of light in a vacuum, as measured by any non-accelerating observer, is the same regardless of the motion of the source or the observer. Using this principle along with the idea of relativity, Einstein formulated the special theory of relativity. In this theory, the speed of light, often represented by the letter c, became a fundamental constant of nature, appearing in equations even when light itself was not directly involved. This revolutionary idea made the concept of a stationary ether unnecessary, and completely transformed our understanding of space and time. During the second half of the 20th century, experimental methods for measuring the speed of light became increasingly precise. Early techniques involved cavity resonance, while later methods relied on laser interferometry. These advances were supported by more accurate definitions of the meter and the second. In 1950, Louis Essen measured the speed of light as 299,792.5 km per second, plus or minus 3 km per second, using cavity resonance. This value was adopted by the 12th General Assembly of the International Radio Scientific Union in 1957. In 1960, the meter was redefined based on the wavelength of a specific spectral line of krypton-86, and in 1967, the second was redefined using the hyperfine transition of the ground state of cesium-133. By 1972, researchers using laser interferometry at the United States National Bureau of Standards in Boulder, Colorado, determined the speed of light in vacuum to be exactly 299,792,456.2 meters per second, with an uncertainty of only plus or minus 1.1 meter per second. This measurement was 100 times more precise than previous values, with the remaining uncertainty mostly due to the definition of the meter. Subsequent experiments confirmed this value, and in 1975, the 15th General Conference on Weights and Measures recommended adopting 299,792,458 meters per second as the official value. By 1983, the 17th meeting of the General Conference on Weights and Measures recognized that defining the meter through a fixed value of the speed of light, combined with the previously established definition of the second, produced far more reproducible measurements than previous methods. The meter was then redefined as the distance light travels in vacuum during a time interval of 1 divided by 299,792,458 of a second. As a result of this definition, the speed of light in a vacuum became exactly 299,792,458 meters per second, and was established as a defined constant in the International System of Units. Subsequent improvements in experimental techniques no longer changed this value, but instead allowed scientists to measure the meter even more precisely by observing the wavelengths of krypton-86 and other light sources. In 2011, the General Conference on Weights and Measures announced plans to redefine all 7 base SI units using an explicit constant formulation where each unit is tied to an exact value of a fundamental constant, just as had been done for the speed of light. This led to a new, fully equivalent wording of the meter's definition. The meter, symbol m, is the unit of length, and its magnitude is set by fixing the speed of light in vacuum to exactly 299,792,458 meters per second. This change was fully incorporated into the 2019 revision of the SI, known as the new SI. The idea of travelling to the stars has fascinated humans for hundreds of years, long before we even had the tools to leave our own planet. Long ago, people looked up at the night sky, amazed by the countless tiny lights scattered across the darkness, and wondered what it would be like to reach those faraway points of brightness. Stories and myths full of cosmic journeys and trips among the stars were common in many ancient cultures, yet they were purely imaginative, part of dreams rather than real plans. Humans have always been curious about the unknown, and the stars represented the biggest unknown, a huge sea of possibilities that no ship at the time could ever hope to sail. As the years passed, these imaginative stories slowly became what we now call science fiction, which began to turn dreams into tales that sometimes hinted at real science. In the early 1800s, books started to explore trips beyond the Earth in more organised ways. Writers such as Jules Verne and H.G. Wells began to describe travel between planets using the science known in their time, though it was still mostly guesswork. Jules Verne, in books like From the Earth to the Moon, written in 1865, imagined a giant cannon shooting a projectile carrying human passengers toward the moon. While the physics of such an idea were impossible by today's understanding, Verne's ideas were remarkable because they tried to combine imagination with scientific reasoning, using the knowledge of the time to inspire awe. H.G. Wells, in his 1898 classic The War of the Worlds, explored not humans travelling to other worlds, but the idea that beings from faraway planets could come to Earth. In doing this, he turned the imagination outward, showing the stars not just as destinations, but as homes to other life and civilizations, further increasing humans' curiosity about space. These books planted the seeds for serious thinking about travel to the stars, showing that ideas of star travel could be discussed in a somewhat scientific way, even if the technology was nowhere near ready. By the early 1900s, science had advanced a lot. Ideas about rockets, physics, and space started to grow, and a few forward-thinking people began moving the idea of travelling to the stars from fiction toward real scientific proposals. One of the most important figures in this was Konstantin Tsiolkovsky, a Russian scientist and engineer born in 1857. Tsiolkovsky is often called the father of space travel because he was among the first to describe in math the principles that could make space travel possible. In 1903, he published his now famous work, The Exploration of Cosmic Space, by means of reaction devices, in which he introduced the rocket equation, a formula showing how rockets could escape Earth's gravity. While Tsiolkovsky mostly focused on reaching Earth orbit and other planets in our solar system, his ideas laid the foundation for the possibility of going beyond the solar system one day. He thought about spacecraft powered by solar sails, a concept still studied today, and imagined multi-generational ships that could carry humans across huge distances to other stars, even if such trips would take centuries. His work changed space travel from a dream into something that could, at least in theory, be built. Around the same time, in Germany, another forward-thinking person, Hermann Oberth, was developing similar ideas. Born in 1894, Oberth published The Rocket into Interplanetary Space in 1923, which explained not only the basics of rockets, but also the possibility of humans exploring planets, and, by extension, stars. Oberth thought about using nuclear energy for propulsion, knowing that regular chemical rockets might never be enough to reach other star systems. His work, together with Tsiolkovsky's, inspired a generation of engineers and scientists, many of whom later helped with the early space programs in the mid-20th century. The years between the world wars, especially in Europe, became a time of fast imagination and ideas about leaving Earth, and these scientific proposals were based on both solid math and the imaginative spark of science fiction. The United States also helped early ideas about travelling to the stars. In the 1930s and 1940s, scientists like Robert Goddard started testing liquid-fueled rockets, which were much stronger than earlier solid-fuel rockets. Goddard, born in 1882, dreamed of sending rockets to the moon and even to the planets, setting up the practical groundwork for space exploration. Though Goddard's focus was first inside the solar system, his experiments showed that controlled propulsion and navigation in space were possible, providing the first steps toward any future trips to other stars. His work received mixed reactions at the time, with some newspapers making fun of his ideas, but it eventually became the base for the space age. After the Second World War, interest in travelling to the stars grew, along with advances in rockets and nuclear physics. The development of long-range missiles during the war, including the German V-2 rocket, gave engineers real examples of controlled propulsion over long distances. Scientists who worked on these projects, including Wernher von Braun, started thinking about how the same ideas could be used for space travel. By the 1950s, proposals for travelling to other stars were appearing in scientific journals, often based on ideas of nuclear propulsion or very efficient engines that could almost reach the speed of light. Ideas like the Bussard ramjet, suggested by physicist Robert W. Bussard in 1960, imagined spacecraft that could collect hydrogen from space to fuel a nuclear engine, allowing them to travel far beyond the solar system without carrying too much fuel. These ideas were bold, almost at the edge of what technology could do, but they were based on scientific reasoning rather than pure imagination. At the same time, science fiction becoming popular helped inspire both public interest and scientific thinking about trips to other stars. Writers like Isaac Asimov, Arthur C. Clarke, and Poul Anderson wrote stories about long-distance space travel, generation ships, and encounters with alien life. Clarke, born in 1916, famously suggested using geostationary satellites for communication in 1945, showing his talent for predicting future technology. In his stories, he often explored how humans might one day reach other stars, mixing careful scientific thinking with exciting storytelling. Science fiction became more than entertainment. It became a playground for ideas, where writers and readers could explore the consequences of human travel across light years. The mix of imagination and scientific thinking during this time helped make travel to other stars a serious topic of discussion, not just a fantasy. By the 1960s, scientists began to carry out more detailed and number-based studies of travel between stars. Projects like Project Orion, started in 1958, looked at the possibility of using nuclear explosions to push a spacecraft, a method called nuclear pulse propulsion, where carefully controlled explosions could send a ship at extremely high speeds. The idea was very bold. A spacecraft could, in theory, be sped up to a large part of the speed of light, making travel to nearby stars, though still taking decades or centuries, possibly doable. At the same time, studies of the limits set by relativity and energy needs helped make ideas about what was really possible more clear. It became obvious that travelling between stars would need technologies far beyond regular rockets, maybe including engines using antimatter or light sails powered by strong lasers, ideas scientists were only beginning to explore in theory. These studies marked a shift from just imaginative ideas to serious physics-based planning, even if making it real was still many decades away. The time also saw the start of thinking experiments about the social and moral effects of journeys between stars. Ships designed for many generations, for example, would need communities that could survive for hundreds of years without contact with Earth. Writers and scientists thought about the mental, social, and biological problems of such trips, including how humans might adapt to closed environments and limited resources over many generations. These points showed that interstellar travel was not just a technical problem, but also a deeply human one, involving culture, ethics, and survival. Early proposals started to look at the big picture, realizing that the problems of reaching the stars were as much social as technical. In the 1970s and 1980s, space agencies began looking into the possibility of sending probes between stars, even if trips with humans were still far off. The Voyager spacecraft, sent in 1977, were built to leave the solar system and eventually enter interstellar space. While they would not reach another star for tens of thousands of years, the idea of sending objects beyond our solar system excited both scientists and the public. These missions showed that humanity could at least start to connect our solar system with the wider galaxy, giving valuable information about the space between stars and the challenges of long trips in space. Even robot missions became part of the larger story of interstellar exploration, proving that going beyond our nearby space was not just a dream. The move from science fiction to real scientific plans continued as new technologies and ideas came up. Laser propulsion, solar sails, and fusion engines became common topics in academic writing, while thinkers like Freeman Dyson and Carl Sagan guessed at the long-term possibilities of reaching other stars. Dyson, born in 1923, suggested huge space habitats and energy-gathering structures that could support long trips, while Sagan, born in 1934, shared ideas of humans as a space-travelling species able to spread across the stars. Their writings connected imagination and practical science, inspiring generations of engineers, physicists, and dreamers to seriously think about what once seemed impossible. Even in the early 21st century, the spirit of these early ideas lived on. Projects like Breakthrough Starshot, announced in 2015, aim to send tiny, laser-powered probes to the nearest star system, Alpha Centauri, within a human lifetime. This modern project continues the line of thought that goes from Jules Verne's Cannon to Tsiolkovsky's equations, Oberth's rocketry, and the nuclear propulsion studies of the 1950s. It shows that the line between imagination and scientific possibility keeps moving outward as technology grows. Ideas that once seemed pure fantasy are slowly becoming real plans, even if practical interstellar travel for humans is still far away. The path from early guessing to serious study shows a lot about the human mind and our lasting desire to go beyond what seems possible. At every stage, from ancient myths to modern plans, humans have mixed imagination, curiosity, and scientific thinking to push the limits of what can be imagined. The process shows how fiction can inspire science and how careful study and experiments can turn dreams into serious questions. Travelling between stars while still beyond our technology has become a real field of study, showing humanity's lasting fascination with the stars. Following this history, one can see the power of ideas to guide exploration, the mix of culture and technology, and the unending human desire to reach places no one has yet visited. Even as the 21st century goes on, the same themes continue. Every new step in physics, engines, or material science opens small doors to reaching nearby stars. Ideas that were once only stories are now studied in scientific workshops and journals, with engineers and theorists figuring out paths, ways to move, and energy needs. While practical human travel between stars is still a huge challenge, the path from science fiction to first serious proposals shows a strong thread of thought, proving that what starts as imagination can, over time, become a plan for real exploration. The earliest ideas of interstellar travel, coming from myths, stories, and guessing, have grown into a field where physics, engineering, and creativity meet, hinting at a future where humans might one day reach the stars, just as we've always dreamed. The fascination with stars has never faded, and each generation of scientists and dreamers builds on the work of those before. Early 20th century thinkers, inspired by the imaginative books of the 19th century, set the groundwork for engineering and physics solutions that might one day make interstellar travel real. Even today, when ideas like warp drives or antimatter engines are studied in theory, they come from the early mix of science and imagination that first made humans think they could one day leave Earth. In this way, the story of interstellar travel is not just about technology, rockets, or physics formulas. It is about human curiosity, ambition, and the lasting drive to explore the unknown. Every story, every formula, and every plan represents a step toward a future where the stars are not just points of light in the night sky, but places we could actually reach. Human fascination with the stars is far deeper than simple curiosity. Since the earliest days of civilization, people have looked up at the night sky with wonder and longing, as if the tiny sparkling lights above held answers about their place in the vast universe. For centuries, this feeling grew into a powerful desire not only to understand the cosmos, but to journey into it, to go beyond the familiar boundaries of our own world. The idea of leaving Earth behind, of finding a new home among the stars, has moved from the realm of myths and stories into a serious question at the heart of modern space exploration. Yet one unchanging truth remains. Travelling to another star only matters if there is a world capable of supporting human life. Without another Earth-like planet to settle on, the dream of leaving our home is just a beautiful idea without a practical destination. The search for such worlds begins by understanding what makes Earth so special. Our planet is a delicate mix of conditions that together create a stable environment for life. It has liquid water, a protective atmosphere, a magnetic field shielding it from deadly solar radiation, and a climate that has remained fairly steady for millions of years. These qualities are rare in the universe, and finding a planet that matches Earth in all these ways is a huge challenge. Every detail counts. Even a small difference could mean the difference between a flourishing ecosystem and a lifeless desert. Scientists call this perfect set of conditions the habitable zone, or sometimes the Goldilocks zone, because it is not too hot, not too cold, but just right for life to survive. This zone is usually determined by how far a planet is from its star, allowing liquid water to exist on its surface. But true habitability requires much more. The planet's makeup, the density of its atmosphere, the availability of essential chemicals, and even the stability of the star it orbits all matter for life to exist and evolve. For decades, astronomers have dreamed of finding planets in these habitable zones around other stars. In recent times, the dream has turned into reality. With the launch of advanced telescopes and space observatories, such as the Kepler Space Telescope in the year 2009, scientists began discovering thousands of exoplanets, planets orbiting stars beyond our Sun. Each new world brought excitement and new questions, as researchers examined whether any could resemble Earth. Some of these planets were super-Earths, larger than our planet but possibly rocky, while others were massive gas giants like Jupiter or Saturn, unlikely to host human life. Each discovery helped refine the methods and criteria used to identify potential new homes for humanity. Yet the challenge is immense. Even with the most advanced technology, most of the planets we can detect lie hundreds or even thousands of light-years away. The enormous distances involved make it clear that only a truly habitable planet could justify the enormous risks, time, and resources needed to reach it. One of the closest and most promising targets is the Alpha Centauri system, about 4.5 light-years from our Sun. This system has 3 stars, Alpha Centauri A and B, which are similar to our Sun, and Proxima Centauri, a smaller red dwarf. In the year 2015, astronomers announced the discovery of an Earth-sized planet orbiting Proxima Centauri within its habitable zone. The news electrified the scientific community, showing for the first time that a potentially habitable world might exist so close to our solar system. But being nearby does not guarantee habitability. Proxima Centauri is an active star, often sending out powerful flares and radiation that could strip away a planet's atmosphere or make life difficult. Even so, the discovery of Proxima b, as it is called, reignited discussions about humanity's interstellar dreams and the technology needed to reach even the nearest star systems. Another fascinating target is Barnard's star, a red dwarf about 6 light-years from Earth. Scientists have studied it closely because it is near and relatively calm. In the year 2018, astronomers found a planet orbiting Barnard's star several times the mass of Earth. Larger planets can hold on to their atmospheres better and retain heat longer, but there is still no certainty that this world could maintain liquid water or a friendly environment for humans. The search around stars like Barnard's star continues to grow, using more advanced techniques that detect tiny shifts in a star's motion or faint dimming as planets pass in front of their stars. Each new discovery adds another clue to the puzzle of where humanity might one day travel beyond our solar system. Finding a truly habitable world involves more than just spotting a planet at the right distance from its star. Scientists must study its makeup, atmosphere, climate, and potential for life. This means analysing starlight passing through a planet's atmosphere, looking for chemical fingerprints of water, oxygen, methane, and other molecules essential for life. But even the presence of these molecules does not guarantee habitability. Some planets, like Venus, have thick carbon dioxide atmospheres, but their surfaces are hot enough to melt lead, with crushingly high pressure. Others, like Mars, show evidence of water in ice and ancient rivers, but its thin air and harsh radiation make long-term human life extremely difficult. Comparing these worlds to Earth highlights how delicate and rare the conditions for life are, showing that finding another planet capable of supporting humanity is far from simple. Beyond the technical problems, the search for planets that could support life also raises a deeper question. Why do humans want to leave Earth at all? Part of the answer comes down to survival. Humanity has faced countless natural disasters, from supervolcanoes and asteroid impacts to climate changes and pandemics. While these events have shaped life on our planet, they also remind us that our existence depends on a single world. The idea of spreading human civilization to other planets offers a kind of safety, making sure life could continue even if Earth became uninhabitable. But survival is not the only reason. Humans are explorers by nature, driven by curiosity, imagination, and the urge to go beyond limits. The stars represent both a challenge and a promise, giving us a chance to grow our knowledge, technology, and perspective in ways Earth alone cannot. Travelling between stars, however, is not just a matter of wishful thinking. The distances between stars are enormous. The nearest star system, Alpha Centauri, is more than 25 trillion miles away, a distance almost impossible to imagine in everyday life. At the speeds of today's spacecraft, it would take tens of thousands of years to reach even the closest star. This has led scientists and engineers to explore advanced propulsion ideas, including nuclear fusion drives, antimatter engines, and light sails pushed by lasers. Each idea promises faster travel, possibly reducing the journey to decades or centuries instead of thousands of years, but each also comes with huge technical challenges. The thought of building spacecraft that can support human life for such long trips adds another layer of difficulty, since life support systems would have to work perfectly for decades or centuries, or multiple generations of humans would have to live and die in space. Finding a planet that could support life is the key to all these plans. Without a suitable destination, the risk and effort of interstellar travel would be pointless. A planet that cannot support humans would turn the journey into a tragic trip with no reward. Even if humans could survive in artificial habitats on board the spacecraft, long-term settlement would need a planet with resources, fertile soil, water, and a stable environment. Terraforming, changing a planet to make it livable, is often discussed in science fiction, but in reality it is a massive task that requires technology we do not yet have. The closer a planet is to Earth's conditions, the easier human settlement becomes, which is why astronomers focus so much on finding Earth-like planets, worlds that are very similar to our own. The search for such planets has sped up in recent years thanks to missions like the Transiting Exoplanet Survey Satellite, or TESS, launched in the year 2018. TESS scans the entire sky for planets by spotting tiny drops in the brightness of stars as planets pass in front of them. Its observations have already led to the discovery of hundreds of exoplanets, some in the habitable zones of their stars. The James Webb Space Telescope, launched in the year 2021, has further improved the search, allowing scientists to study the atmospheres of distant worlds in great detail. These tools represent the next generation of technology that might finally answer the age-old question: are we alone? And if not, where else could life exist? Even as scientists find potentially habitable planets, the problem of distance remains. The closest ones are light years away, and even if future propulsion technology makes travel faster, interstellar missions will probably still take many generations. This raises questions about who would travel, how communities would work in space, and what long journeys would do to humans socially and mentally. Life on a starship cut off from Earth for decades or centuries would need social systems, governance, schools, and entertainment to keep people healthy and happy. Planning such a journey needs imagination, foresight, and careful thinking about both technology and human needs. Another issue is the long-term stability of the destination planet. Stars change over millions or billions of years, affecting their brightness, radiation, and habitable zones. A planet that is livable today might not stay that way in the distant future, especially if its star is prone to sudden flares or slow brightening. Red dwarf stars like Proxima Centauri and Barnard's star last a long time but are often very active, while sun-like stars are more stable but live shorter lives. The window for human settlement may be limited, requiring careful choice and timing. As humans keep looking for habitable worlds, the effort brings together many areas of science, technology, and philosophy. Astrophysicists calculate orbits and model atmospheres, biologists study what life needs, engineers design spacecraft able to survive interstellar travel, and ethicists and policymakers consider the consequences of sending humans to new worlds. This team effort shows how complex the challenge is, emphasizing that finding another Earth is not just about spotting a planet with water. It's about making sure a new home can support the full richness of human life. The discoveries so far give both hope and caution. Planets like Proxima b, the Barnard star candidate, and many exoplanets found by TESS and Kepler suggest the universe may hold countless worlds, some of which could host life or support humans. Yet, the reality of vast distances and the fragility of life reminds us that the journey will be difficult, requiring patience, creativity, and perhaps generations of humans willing to dedicate their lives to exploration. The balance between what is possible and what is limited drives both science and imagination, inspiring the pursuit of knowledge and the dream of one day standing on the surface of another world. The idea of humans making entire homes in space, instead of endlessly looking for another planet that could support life, is a vision that has fascinated scientists, dreamers, and engineers for many decades. People have long looked up at the stars, wondering whether we are alone, and whether somewhere out there exists a world like our own, full of life and possibilities. Yet the more we explore the vast universe, the clearer it becomes that finding a planet with conditions suitable for humans is unimaginably hard. The distances are almost impossible to imagine. Even the closest star system, Alpha Centauri, is more than 4 light-years away, meaning that light, the fastest thing in the universe, takes over 4 years to travel from there to here. If we sent a spacecraft with current technology, it would take tens of thousands of years to reach such a place. With these huge challenges, it becomes clear that the idea of building artificial homes, entire worlds that we design and control ourselves, may not just be a dream, but a need for the survival and growth of our species. From the very beginning, humans have shown an amazing ability to adjust to new environments. From the frozen lands of the Arctic to the deserts of Africa, we have managed to make harsh places livable through cleverness, technology, and sheer determination. The same idea applies to space. While no natural planet may perfectly suit our needs, We have the potential to create controlled environments where temperature, pressure, gravity, and air can be set exactly for humans. Artificial homes could range from huge, spinning space stations that create gravity through centrifugal force to domed colonies on the surfaces of moons or asteroids, each carefully built to protect people from radiation, meteor hits, and the emptiness of space. One of the earliest and most exciting ideas for artificial homes in space was proposed by the famous physicist and space dreamer Konstantin Tsiolkovsky in the early 20th century. He imagined enormous spinning cylinders, sometimes hundreds of meters long, turning in the void of space to create artificial gravity. The spinning would allow people inside to walk, run, and live in conditions similar to Earth. Later, in the 1960s and 70s, scientists such as Gerard K. O'Neill expanded on this idea, imagining huge cylindrical and donut-shaped space colonies that could house thousands or even millions of people. These structures, often called O'Neill cylinders, would have large amounts of farmland, freshwater storage, parks, and cities, basically creating entire ecosystems floating in space. Unlike a distant planet that might take decades or centuries to reach, these homes could be built fairly close to Earth, perhaps orbiting our planet or the Moon, making them much easier to reach and supply. The idea of artificial homes also opens up possibilities that natural planets could never offer. On Earth, life is limited by nature, by the planet's land, climate, and natural disasters. In space, humans could design homes with perfect climates, made-up ecosystems, and even adjustable gravity. Imagine a city where the weather is always mild, rain is exactly measured, and the air is always clean and safe to breathe. Imagine forests and rivers built to maximize beauty and sustainability. In these controlled places, diseases could be handled more easily, food could be grown all year without depending on seasons, and energy could be collected from the sun in ways much more efficient than on Earth. Unlike colonizing another planet, where humans must adjust to harsh conditions, in an artificial home, the environment adjusts to humans. Radiation, one of the biggest dangers in space, can be controlled in artificial homes. On Earth, our planet's magnetic field and thick atmosphere protect us from cosmic rays and solar radiation, but outside these shields, space is dangerous. For humans travelling to Mars or other faraway worlds, being exposed to radiation for a long time could increase the risk of cancer and other health problems. Artificial homes can be built with thick protective walls, water layers, or magnetic shields to copy Earth's protection. Advanced materials, perhaps made in the coming years, could make them even safer, making life in space not only possible, but comfortable and secure. Building artificial homes will definitely need a huge amount of resources, cleverness, and teamwork. Materials might need to be taken from the Moon, asteroids, or other space bodies, reducing the high cost of bringing supplies from Earth. Water could come from ice found on the Moon or asteroids, and sunlight could be focused and brought into the homes to provide energy and warmth. Smart recycling systems would be key, letting every drop of water, every bit of oxygen, and every piece of waste be reused. These systems would not just keep life going, they could make self-sustaining ecosystems where humans, plants, animals, and tiny organisms live in perfect balance, like small versions of Earth. Artificial homes also make us rethink what a world really means. We usually think of planets as natural spheres that hold life, but a home could change that idea completely. Worlds we make could be built for specific purposes: science, industry, learning, or even fun. Cities could float in space, lit by sunlight and artificial lights that copy day and night. Gravity could be different in various zones, maybe letting children play in low gravity while adults have normal Earth-like gravity for health. Ecosystems could be modular, with forests, lakes, and fields designed to support each other. The only limits would be our imagination in a world built from scratch. Another important idea about artificial homes is that they can grow. While there may be only a few Earth-like planets in the whole galaxy, the chance to build artificial homes is almost endless. One cylinder can house thousands, and multiple connected homes can create whole communities in space. These homes could orbit the Sun, forming clusters like small cities or even nations. Populations could grow or move as needed, and the homes themselves could be redesigned and improved over time, something impossible on a natural planet. In this way, making our own worlds could let humanity grow beyond the limits of a single planet, turning space itself into a place for civilization. The mental and social sides of living in artificial homes are also exciting. While humans have evolved to live on one planet, the need to explore and adapt has always been part of us. Space homes would create new chances for culture, art, and social life. Humans might make new languages, customs, and technologies for these special places. Communities could form around shared work and interests, and looking out at the stars from a home could deepen our sense of wonder. Living in a made world could also teach cooperation and careful planning, as the survival of everyone would depend on each person helping to maintain the home. Artificial homes could also act as stepping stones for exploring the universe further. Once humans learn to live in space on a large scale, these homes could be bases for missions to more distant stars. They could become centers of learning, letting humanity test new technologies, study faraway space objects, and grow our knowledge in ways impossible from Earth. A network of connected homes could even serve as a backup for humanity, ensuring the survival of our species if a disaster struck Earth. In this way, artificial homes are not just a way to live in space, they are a way to protect the long-term future of human civilization. The technological challenges of building such homes are huge, but none are impossible. Advances in robotics, artificial intelligence, material science, energy production, and life support systems are slowly making the dream closer to reality. NASA, the European Space Agency, and private companies like SpaceX and Blue Origin are already testing technologies that could one day support long-term life in space. Ideas like inflatable modules, advanced 3D printing and zero gravity, and self-working construction robots are being explored, each bringing us closer to the day when humans will live not only on Earth, but in carefully built worlds among the stars. The vision of artificial homes also changes how we see the universe. Instead of just waiting to find a habitable world, we become active participants, shaping our environment and making life possible wherever we go. This is a big step in human thinking. It is no longer enough to just survive on one planet. We have the potential to become creators of our own destiny, designing worlds that reflect our values, needs, and imagination. The challenge is not only technical but also philosophical. What kind of worlds do we want to make, and how can we make sure they last, are fair, and give good lives for future generations? History shows that humans have always met the challenge of changing their environment. From the first settlements along rivers to the huge cities of today, we have constantly reshaped the world to fit our needs. Artificial homes in space are just the next step in this long journey. They let us reach beyond the limits of Earth, to explore and live in parts of the universe that would otherwise stay out of reach. They also remind us that survival and progress are not passive. They need vision, creativity, and courage. In the vast, dark emptiness of space, a carefully built home can become a light of life, innovation, and hope. One of the most exciting parts of artificial homes is that they solve the problem of limited space. Earth has limited room, resources, and ability to grow. As the global population keeps rising, pressure on natural ecosystems, food production, and energy becomes more serious. Artificial homes could help by giving extra living space, renewable energy, and opportunities for sustainable farming in controlled environments. They could act as experimental zones where new farming methods, energy systems, and waste management strategies are tested and perfected before being used on a whole planet. In this way, these homes are not only places to live in space, but also labs for innovation that can help humanity as a whole. Artificial homes also challenge our ideas about the human body and health. Living in space strongly affects muscles, bones, and circulation. By designing homes with adjustable gravity, humans could stay healthy more easily. Exercise could be part of daily life in creative ways, and medical technologies could be designed for space conditions. Nutrition could be improved, and mental health could be supported through well-designed living spaces, access to nature, and chances for social interaction. Artificial homes could improve life in ways Earth itself cannot always do, mixing the best parts of nature with the benefits of technology. Cosmic rays, also known as astroparticles, are tiny but incredibly energetic particles, or small groups of particles, mostly protons or the cores of atoms, that travel through space at speeds very close to the speed of light. They come from many places. Some are born in the Sun, others originate elsewhere in our Milky Way galaxy, and yet more arrive from galaxies far, far away. When these particles reach Earth and collide with our atmosphere, they create showers of secondary particles. Some of these smaller particles make it all the way to the ground, but most are deflected away by Earth's magnetic field or the protective bubble around the Sun known as the heliosphere. The discovery of cosmic rays is credited to Victor Hess, who in the year 1912 conducted daring balloon flights into the upper atmosphere. His experiments showed that radiation increased with altitude, proving that these energetic particles were coming from outer space. For this groundbreaking work, Hess was awarded the Nobel Prize in Physics in the year 1936. Scientists have been able to measure cosmic rays directly, especially the lower energy ones, since the launch of the first satellites in the late 1950s. These measurements are made using particle detectors, similar to the ones used in high-energy physics laboratories, attached to satellites and space probes. Observations from the Fermi Space Telescope in the year 2013 suggest that a large portion of cosmic rays comes from the explosive deaths of stars, called supernovae. In addition, studies of neutrinos and gamma rays from a distant galaxy known as Blazar TXS 0506+056 in the year 2018 indicate that highly active regions at the centers of galaxies, known as active galactic nuclei, also produce cosmic rays. Looking at the composition of cosmic rays that come from outside Earth's atmosphere, about 99% are stripped down atomic nuclei, meaning they have lost their electrons. The remaining 1% are single electrons, also called beta particles. Among the atomic nuclei, around 90% are just protons, which are the cores of hydrogen atoms. About 9% are alpha particles, which are the same as helium nuclei, and about 1% are heavier atomic nuclei, often called HZ ions. These percentages can vary depending on the energy of the cosmic rays. A tiny fraction of cosmic rays are made of stable antimatter particles, like positrons or antiprotons. Scientists are still actively studying this mysterious fraction, and as of the year 2019, searches for anti-alpha particles in space had not found any clear evidence. When cosmic rays slam into the atmosphere, they smash atoms apart, producing many new particles, including pions and muons, as well as neutrinos. Pions are unstable and quickly decay into muons, which are more stable and can pass through matter easily. This is why muons from cosmic rays can reach deep underground. At airplane altitudes, the neutrons in this cascade of particles can make up between 40 and 80% of the radiation. On the surface of the Earth, muons arrive at a steady rate. Roughly 1 muon passes through a space the size of a human head every second. Together with the natural radioactivity from the ground, these muons cause ionization in the lower atmosphere. This ionization first caught the attention of scientists and eventually led to the discovery of cosmic rays coming from beyond our atmosphere. Cosmic rays are important both practically and scientifically. For astronauts and satellites outside Earth's protective magnetic field and atmosphere, cosmic rays can damage electronics and living tissue. Scientifically, the most energetic cosmic rays, known as ultra-high energy cosmic rays, have been measured with energies approaching 3 × 10 to the power of 20 electron volts. To put this in perspective, this is over 10 million times more energy than the highest energy particles produced by the Large Hadron Collider, which reaches about 7 tera electron volts, or 7 × 10 to the power of 12 electron volts. Theorists suggest that such extreme energies could be reached by a spinning acceleration mechanism near active galactic nuclei. One famous ultra-high energy cosmic ray, nicknamed the OMG particle, and recorded in the year 1991, had an energy of 50 joules, which is roughly equivalent to the kinetic energy of a baseball moving at 90 kilometers per hour, or 56 miles per hour. These discoveries have sparked interest in searching for cosmic rays with even greater energies. However, most cosmic rays are far less energetic, with their energy distribution peaking around 300 mega-electron-volts, or about 4.8 × 10 to the -11 joules. After Henry Becquerel discovered radioactivity in the year 1896, scientists generally thought that the electric charges in the atmosphere, known as the ionization of the air, came only from radioactive materials in the ground, or from radioactive gases like radon released by these materials. Between the years 1900 and 1910, measurements showed that the rate of ionization increased with height above the ground. At the time, this was explained as being caused by the absorption of radiation by the air as it travelled upward. In the year 1909, Theodore Wolff invented a device called an electrometer, which could measure how quickly ions were produced inside a sealed container. Using this device, he discovered that radiation levels were higher at the top of the Eiffel Tower than at its base. Despite this intriguing finding, Wolf's paper, published in the journal Physikalische Zeitschrift, did not gain widespread attention. 2 years later, in 1911, Domenico Pacini made careful measurements of ionization over a lake, over the sea, and at a depth of 3 meters below the water's surface. He noticed that ionization decreased underwater, which led him to conclude that some of the radiation came from sources other than the Earth itself. The breakthrough came in 1912 when Victor Hess took 3 improved Wolf electrometers on a balloon ride to an altitude of 5,300 meters. Surprisingly, he found that the ionization rate at this height was roughly twice as high as at ground level. To rule out the Sun as the source, Hess repeated his measurements during a near-total solar eclipse. Even with the Sun mostly blocked by the Moon, the radiation increased with altitude. Hess concluded that the results of the observations seem most likely to be explained by the assumption that radiation of very high penetrating power enters from above into our atmosphere. Over the following years, from 1913 to 1914, Werner Kohlhörster confirmed Hess's findings by measuring an increase in ionization at altitudes up to 9 kilometers. For his pioneering work, Victor Hess was awarded the Nobel Prize in Physics in 1936. In the year 1931, the renowned physicist Ernest Rutherford commented on the progress, saying that thanks to the meticulous experiments of Professor Millikan and the even broader experiments of Professor Regena, scientists finally had a reliable curve showing how radiation is absorbed in water. During the 1920s, the term cosmic ray was coined by Robert Millikan, who made measurements of ionization caused by these rays from deep underwater to high in the atmosphere, and in many locations around the world. Millikan believed that his data showed that cosmic rays were mainly gamma rays, high-energy photons. He suggested that they were produced in interstellar space as byproducts of hydrogen atoms fusing into heavier elements, with secondary electrons forming in the atmosphere through interactions with these gamma rays. In 1927, while travelling by ship from Java to the Netherlands, Jacob Clay found that cosmic ray intensity was stronger at mid-latitudes than near the tropics. Later experiments confirmed this observation, showing that the Earth's magnetic field deflects cosmic rays, meaning they must carry electric charge and cannot be simple photons as Millikan had proposed. In 1929, Bothe and Kohlhörster discovered that cosmic rays could penetrate more than 4 centimeters of gold, proving that these high-energy particles could not originate from gamma rays alone. By 1930, Bruno Rossi predicted that cosmic rays coming from the east and west would differ in intensity depending on the charge of the primary particles, a phenomenon called the east-west effect. 3 independent experiments confirmed that more rays came from the west, showing that most primary cosmic rays are positively charged. Between 1930 and 1945, many studies established that primary cosmic rays are mainly protons, while the secondary particles they create in the atmosphere are electrons, photons, and muons. By 1948, balloon experiments using nuclear emulsions near the top of the atmosphere revealed that about 10% of primary cosmic rays are helium nuclei, alpha particles, and around 1% are heavier atomic nuclei such as carbon, iron, and lead. During tests for the east-west effect, Rossi also noticed that 2 widely separated Geiger counters sometimes recorded simultaneous discharges far more often than expected by chance. Rossi concluded that occasionally very energetic cosmic ray events produced showers of particles that triggered both detectors at once. In 1937, independently of Rossi, Pierre Auger observed the same phenomenon. He found that primary cosmic rays interact with air molecules high in the atmosphere, creating cascades of secondary particles, including electrons and photons, which reach the ground. In the Soviet Union, physicist Sergei Vernov was the first to carry instruments on balloons to high altitudes to measure cosmic rays using radio sondes. On the 1st of April, 1935, he took measurements up to 13 kilometers and 600 meters, using 2 Geiger counters arranged to avoid counting secondary showers. In the same era, the Indian physicist Homi J. Bhabha, together with Walter Heitler, developed a theoretical explanation for cosmic ray showers. Their classic 1937 paper showed how primary cosmic rays from space interact with the upper atmosphere to produce the particles observed at ground level. They explained that these showers are created by a chain reaction, where gamma rays produce pairs of positive and negative electrons, which in turn produce more gamma rays, cascading down to the Earth's surface. The study of cosmic rays, high-energy particles that travel through space at nearly the speed of light, has a fascinating history full of ingenuity and discovery. The first precise measurements of the energy and directions of the ultra-high-energy cosmic rays were carried out in 1954 by members of the Rossi Cosmic Ray Group at the Massachusetts Institute of Technology. They used two innovative techniques, density sampling and fast timing of extensive air showers, which allowed them to trace the cosmic rays as they struck the Earth's atmosphere. Their experiment took place at the Agassiz station of the Harvard College Observatory and involved 11 scintillation detectors carefully arranged in a circle 460 meters across. This pioneering work, along with many other experiments around the world, revealed that the energies of primary cosmic rays could reach far beyond 100 quintillion electron volts. Building on these early achievements, a massive experiment called the Pierre Auger project was established on the vast pampas of Argentina. This international collaboration, initially led by James Cronin, who had won the Nobel Prize in Physics in 1980 for his work at the University of Chicago, and Alan Watson from the University of Leeds, aimed to investigate the properties and arrival directions of the very highest energy cosmic rays. Today, the observatory continues its work under the guidance of the International Pierre Auger collaboration, undergoing upgrades to improve accuracy and search for the still mysterious origins of the most energetic cosmic rays. These studies are particularly important because of a theoretical limit known as the Greason-Zatsepin-Kuzmin limit, which predicts that cosmic rays travelling from distances of roughly 160 million light-years cannot exceed energies above 100 quintillion electron volts due to their interactions with leftover photons from the Big Bang. Meanwhile, in 1967, high-energy gamma rays, photons with energies greater than 50 million electron volts, were discovered in cosmic radiation through an experiment conducted on the OSO-3 satellite by scientists at MIT. These gamma rays were much less intense than the charged particles, making up less than 1% of the total cosmic radiation, and originated from both within our galaxy and beyond. Since then, successive gamma-ray observatories in space have mapped the sky in unprecedented detail. The most recent, the Fermi Observatory, revealed a narrow band of gamma-ray intensity within the Milky Way, produced by both discrete and diffuse sources, along with numerous point-like sources from distant galaxies scattered across the heavens. The intensity of cosmic rays that reach Earth is not constant, but is influenced by the Sun. The solar wind and the Sun's magnetic field affect how cosmic rays move through the heliosphere, the vast bubble of charged particles surrounding our solar system. This effect, known as solar modulation, causes the intensity of cosmic rays to rise and fall in roughly 11 and 22-year cycles, linked to the rhythm of solar activity. To understand how cosmic rays travel and gain energy, physicists use a mathematical tool called the Parker transport equation, named after Eugene Parker. This equation models how energetic particles move and accelerate through space, including both their positions and momenta. It has been used to study cosmic rays accelerated by shock waves from supernova remnants, by coronal mass ejections from the Sun, and at the boundary where the solar wind meets interstellar space. By understanding these processes, scientists can better grasp how cosmic rays acquire the extraordinary energies they possess. The quest to identify the sources of cosmic rays began almost a century ago. In 1934, astronomers Walter Baird and Fritz Zwicky proposed that cosmic rays might come from supernova explosions. 14 years later, in 1948, Horace W. Babcock suggested that magnetic variable stars could also produce cosmic rays. Then, in 1951, Sakido and colleagues identified the Crab Nebula as a cosmic ray source. Over time, other possible sources emerged, including active galactic nuclei, quasars, and gamma-ray bursts, creating a complex and fascinating cosmic puzzle. Modern observations have helped narrow down the origins of these enigmatic particles. In 2009, scientists at the Pierre Auger Observatory presented evidence that some ultra-high-energy cosmic rays came from a region of the sky near the radio galaxy Centaurus A, although further research was needed to confirm this. Interestingly, no connection was found between cosmic rays and gamma-ray bursts, placing strict limits on how much cosmic rays could come from these energetic explosions. Around the same time, supernovae were suggested as a confirmed source of cosmic rays based on data from the Very Large Telescope. However, this was challenged in 2011 by observations from the Pamela satellite, which revealed unexpected differences in the energy spectra of hydrogen and helium cosmic rays, suggesting that their origins were more complicated. Later, in February 2013, Fermi satellite observations of neutral pion decay confirmed that supernovae indeed produce cosmic rays, with each explosion generating roughly 3 × 10 to the 42 to 3 × 10 to the 43 joules of cosmic ray energy. Even so, supernovae do not account for all cosmic rays, leaving open questions about how other cosmic accelerators, like active galactic nuclei, contribute to the total cosmic ray flux. Physicists explain the acceleration process using the concept of shock front acceleration, where atoms stripped of their electrons are propelled to tremendous speeds by powerful cosmic shock waves. In 2017, the Pierre-Auger collaboration reported a subtle directional pattern, or anisotropy, in the highest energy cosmic rays. Since this pattern shows a deficit in the direction of the center of the Milky Way, it suggests that these ultra-high energy cosmic rays mostly come from outside our galaxy. This discovery points to the existence of a transition energy between cosmic rays originating within the Milky Way and those from more distant galaxies, implying that different sources contribute to different ranges of cosmic ray energies. Cosmic rays are fascinating travelers from space, and they come in 2 main types, primary and secondary. Primary cosmic rays are the original particles created in different energetic events across the universe. Most of these primary cosmic rays, about 99%, are protons and helium nuclei, also called alpha particles. A tiny fraction, roughly 1%, consists of heavier atomic nuclei, while an almost unmeasurable amount is made of antimatter particles such as positrons and antiprotons. When primary cosmic rays smash into the Earth's atmosphere, they trigger a chain reaction, producing secondary cosmic rays. These secondary particles include photons, various types of hadrons, and leptons such as electrons, positrons, muons, and pions. Interestingly, the electrons, muons, and pions were first discovered thanks to these cosmic ray interactions. Most primary cosmic rays come from beyond our solar system, and sometimes even from outside the Milky Way galaxy. When they strike Earth's atmosphere, they transform into secondary particles. Looking at their composition, the ratio of helium to hydrogen nuclei in cosmic rays is about 28%, which closely matches the early universe's ratio of 24%. The rest is made up of heavier nuclei, usually the byproducts of nuclear processes, including lithium, beryllium, and boron. These light elements appear in cosmic rays far more frequently, around 1%, than in the Sun's atmosphere, where they are almost 1,000 times less common compared to helium. Cosmic rays that include nuclei heavier than helium are called Hz ions. Even though they are rare, these Hz ions are highly charged and massive, meaning they contribute significantly to radiation exposure for astronauts in space. The reason these rare elements are more abundant in cosmic rays is due to a process called spallation. As cosmic rays made of carbon and oxygen travel through interstellar space, they collide with dust and gas, breaking apart into lighter elements such as lithium, beryllium, and boron. This same process also creates small amounts of scandium, titanium, vanadium, and manganese when iron and nickel nuclei crash into interstellar matter. At extremely high energies, the composition of cosmic rays changes, and heavier nuclei become more common in certain energy ranges. Scientists continue to study cosmic rays with great precision to understand this composition at higher energies. Satellites have even found a small number of positrons and antiprotons in primary cosmic rays, making up less than 1% of the total. These particles are not signs of vast amounts of antimatter left over from the Big Bang or hidden complex antimatter in the universe. They are simply individual particles created in highly energetic cosmic events. The Alpha Magnetic Spectrometer, AM02, currently operating on the International Space Station, has shown that these positrons arrive from all directions without any preferred path. In September of 2014, researchers presented almost twice as much data at CERN, which was later published in Physical Review Letters. They measured the positron fraction in cosmic rays up to 500 gigaelectronvolts, finding that it peaks at about 16% of the total electron plus positron events, around an energy of approximately 275 gigaelectronvolts, give or take 32 gigaelectronvolts. At energies above 500 gigaelectronvolts, the ratio of positrons to electrons begins to decline. The absolute number of positrons also decreases before 500 gigaelectronvolts, But interestingly, the peak energies for positrons are much higher than those for electrons, which peak near 10 gigaelectronvolts. Some scientists suggest that these high-energy positrons could be the result of massive dark matter particles annihilating each other. Antiprotons in cosmic rays also behave differently. They have much higher average energies than normal protons, peaking around 2 gigaelectronvolts, suggesting they are made in entirely different processes from ordinary cosmic ray protons, whose average energy is only about 1/6 of this. So far, no complex antimatter nuclei, like antihelium, the antimatter version of helium nuclei, have been found in cosmic rays, though scientists are actively searching for them. Earlier, a prototype of AM02, called AM01, flew on the Space Shuttle Discovery during mission STS-91 in June of 1998. It did not detect any antihelium, establishing an upper limit of roughly 1.1 millionths for the antihelium to helium ratio in cosmic rays. When cosmic rays enter the Earth's atmosphere, they collide with oxygen and nitrogen atoms, triggering what is known as an air shower. This cascade produces a wide variety of secondary particles, including X-rays, protons, alpha particles, pions, muons, electrons, neutrinos, and neutrons. Most of these secondary particles continue travelling in a path very close, within about 1 degree, to the original trajectory of the cosmic ray that struck the atmosphere. Common products of these collisions include neutrons and charged mesons, like positive and negative pions and kaons. Some of these particles decay into muons and neutrinos, which can reach the Earth's surface. High-energy muons can even penetrate shallow mines, while neutrinos often pass through the entire planet without interacting. Other particles decay into photons, which trigger further electromagnetic cascades. As a result, photons, electrons, and positrons usually dominate in these showers. Scientists can detect them using instruments such as cloud chambers, bubble chambers, water Cherenkov detectors, or scintillation detectors. Observing a secondary shower of particles across multiple detectors at the same time is a clear sign that they all originated from the same cosmic ray event. Cosmic rays hitting other planets or moons in our solar system are usually detected indirectly, through high-energy gamma rays observed by gamma-ray telescopes. These can be distinguished from normal radioactive decay by their much higher energies, typically above 10 million electronvolts. There are two main ways scientists detect cosmic rays. The first is direct detection, where the primary cosmic rays are measured in space, or at very high altitudes using instruments carried by balloons or satellites. The second is indirect detection, which involves measuring the secondary particles produced when cosmic rays hit Earth's atmosphere, creating what is called an extensive air shower. Although there have been ideas and prototypes for detecting air showers from space or high-altitude balloons, current experiments that study high-energy cosmic rays mostly take place on the ground. In general, direct detection gives more accurate results than indirect detection. However, cosmic rays become much rarer at higher energies, which makes direct detection difficult for energies above 1 peta-electronvolt. Both direct and indirect methods use a variety of techniques to capture cosmic ray data. Direct detection can be done with many types of particle detectors placed on the International Space Station, satellites, or high-altitude balloons. However, weight and size limits restrict which detectors can be used. One well-known method of direct detection was developed by Robert Fleischer, P. Buford Price, and Robert M. Walker for use on high-altitude balloons. This method uses plastic sheets, such as 0.25 mm thick Lexan polycarbonate, stacked together and exposed to cosmic rays in space or at high altitudes. When a cosmic ray passes through the plastic, its nuclear charge breaks chemical bonds or ionizes the material. At the top of the stack, the cosmic ray is moving very fast, so ionization is small. As it slows down while passing through the stack, ionization increases along its path. After exposure, the plastic sheets are treated in a warm caustic sodium hydroxide solution, which slowly dissolves the plastic. The solution dissolves the ionized areas faster than the rest, creating small conical pits in the plastic. Scientists then measure these pits under a high-power microscope, usually magnified 1600 times with oil immersion, and plot the etch rate as it changes with depth in the stack. This method produces a unique curve for each type of atomic nucleus, from 1 to 92, allowing researchers to determine both the charge and energy of the cosmic ray that passed through the stack. The more ionization along the path, the higher the charge of the particle. Beyond cosmic ray studies, this technique is also used to detect nuclei formed in nuclear fission experiments. On the ground, there are several methods for detecting cosmic rays, which fall into two main groups: detecting the secondary particles from air showers using particle detectors, and detecting the electromagnetic radiation that air showers emit in the atmosphere. Extensive air shower, EAS arrays, are collections of particle detectors that measure the charged particles passing through them. These arrays can monitor a wide area of the sky and work more than 90% of the time. However, they are not as good at separating cosmic ray signals from background noise as Air-Cherenkov telescopes. Modern EAS arrays usually use plastic scintillators, while some use water or ice as a medium to produce Cherenkov radiation when particles pass through. Many arrays combine different detectors, which allows them to distinguish muons from lighter secondary particles like photons, electrons, or positrons. The proportion of muons in a shower is one common way to estimate the mass of the original cosmic ray. A historic method, still used for teaching and demonstration, involves cloud chambers, which can detect muons created when pions decay. Cloud chambers are easy to build with simple materials, even in a high school laboratory. Another method uses bubble chambers to detect cosmic ray particles. More recently, CMOS sensors in everyday smartphone cameras have been suggested as a large, distributed network for detecting air showers from ultra-high energy cosmic rays. The first app designed for this idea was called Crayfizz, short for cosmic rays found in smartphones. In 2017, the Credo collaboration released the first version of a fully open-source app for Android phones. Since then, the project has gained interest and support from many scientific and educational institutions, as well as members of the public around the world. Future studies will determine how well this new approach can compete with traditional, dedicated EAS arrays.